Hey everyone, so today we are going to be implementing the rest of the transformer model. So as a quick recap, in the first video we did a super deep dive into attention, just to understand all the variants that you see attention in. Regular attention, attention with padding masks, we looked at causal attention, and we looked at cross attention. And we're going to need to put all of these things together to perform our machine translation task. And in the next video, we looked at preparing the data set. So we're going to pick up right off from where we left, but let's just quickly recap again. If we do Python data.py, right? This is the data set that we prepared. Basically, as you can see, we have source input IDs. These are going to be our input English, already pre-tokenized and ready to go because we cleaned that data set, prepped it, and everything last time. So we have our source input IDs. We have its corresponding mask, right? Because different sentences are of different lengths. So we need to make sure we add a padding mask to not attend to these extra pad tokens that we add in. Again, if you're a little bit confused about what these padding masks exactly are, then please just go take a look at those previous videos. We also need to do, we have our input French starting with our beginning of sentence token. And we have our output, right? The thing that we want to predict. And basically this is just offsetted by 1. So if you look at our input, it goes 26842, 22651. And notice our output is 6842, 22651, ... So it's the same thing, just offsetted by 1. And we have the corresponding mask for our French as well, right? Because we have different French sentences are of different lengths. So we need to make sure we pad them accordingly and ensure we don't actually attend to those pad tokens. So now that we have all this, let's go ahead and just begin our implementation. So to implement this model, there's a couple things that we are going to need. So first, we're only going to be using torch basically for all of this. So import torch.nn as nn, import torch.nn.functional as f. And we're going to do from data classes, import data class. So if you don't know what data class is, it makes life very simple. Transformer config. I just like writing simple config function or config classes to effectively let us just, set up the structure of the model this way. You can do it however you want, but let's kind of set the important stuff that we need. First, the embedding dimension. So how many numbers do we want to use to represent every single token? And by default, the attention is all you need paper used 512, so we're going to use 512. Then we're going to do num attention heads. How many heads of attention do we want? Again, if you don't know what this is, just watch my attention video. We go into it in quite a bit of depth. So there we go. And not 0, we want 8 attention heads. We then want attention dropout p. So this is going to be our dropout. By default, when we're doing training on large data sets, we don't typically apply dropout all that much. Dropout's more necessary when we're fine-tuning for something else, and we can see that later. Hidden dropout p. This is going to be on the fully connected layer, which we'll see later. We have a MLP ratio, which won't mean anything now, so we're going to not talk about this until we actually use it. And then we have our encoder depth, and now's actually a good time to pull this up. So this is the figure we were looking at. In the first video, we implemented all the orange boxes, right? We have basically multi-head attention, we have causal attention, and we have cross attention. So all of these have been implemented. What we haven't implemented is basically these feed-forward modules and just kind of wrapping it all together nicely in a transformer block. And we also need these positional encodings and these input-output embeddings. So we're going to implement all of these pieces one at a time. But notice here there's a n times, right? So how many encoder transformer blocks do we want? How many decoder transformer blocks do we want? And we just have to set that ahead of time. And by default, we're going to use 6, right? I think that's what the original paper used, so we're going to use 6. So our encoder depth is going to be 6. How many transformer encoders do we want? And then our decoder depth int is also 6. How many transformer decoders do we want? Now that we have that, there's a couple other small pieces of information. Source vocab size. So if you remember, in the last video, we trained a tokenizer for French but we're just using the default BERT tokenizer for English. I only trained the French tokenizer just to show like how would you go about making your own tokenizer if you needed to. But for the English purpose, we're just using a BERT tokenizer, and I know the BERT tokenizer has 30,522 tokens in it, so that's what we're using. Our target vocab size, the tokenizer we trained for French, I trained it to have 32,000 tokens, so there we go, 32,000 tokens. And then max source len, how many tokens am I willing to accept total? And so I'm willing to do 512 tokens in the encoder. And then max target len, this is also going to be in. I'm willing to have 512 tokens in the French as well. So 512 English, 512 French, and that's the maximum sequence length that I'm willing to process. This is obviously a very short sequence length. State-of-the-art models today have ridiculous context sizes that cross like hundreds of thousands, but this is just to give the general idea of what's going on. And we're going to do learn, pause, embed. And so we're going to talk about positional encodings in just a second. But this is whether or not we want a learnable or a non-learnable positional encoding. So we're going to do class. So we're going to implement positional encoding now. It's a good time to talk about it. So the problem with transformers is this. It has this feature, not really feature, it's not a bug either, it's just how it is, called permutation. Invariant. This means transformers don't actually care about the sequence of the text, or any sequence that we're working on. And that's probably a problem, right? If it doesn't care about the order of our sequence, then haven't we lost the sequence problem, right? Like the order of words in text matters quite a bit about what that text means. Like how you position the words and how they are related to each other in position can greatly affect what that sentence is trying to say. So how do we deal with this? And why does this happen? So first of all, we know that data for our transformer, let's ignore the batch dimension for now. We know it's going to be some sequence length by embedding dimension, right? So we'll have some sequence length, and every token in the sequence is represented by some vector. And let's call this S1, S2, S3, right? And we're going to convert this with queries, keys. And this is going to be a value as well, but we should be able to get the point across with just a Q and K. And this is going to produce another sequence by embedding up here that'll have the first query, right, the second query, and the third query. And then similarly, we're going to make our keys, which will again be sequenced by embedding, and this will have the first key, which corresponds with the first token, and then the second key that corresponds to the second one, and then the third key that corresponds with the third one. And now I just do my Q, K, transpose operation. And the question I want to ask is that, does the position matter? For example, if I'm doing, so this would look like a sequence by embedding. So this will be Q1, Q2, Q3. Oh, that's terrible. Let's fix that. Q3 times a K1, K2, K3, because we transposed it, right? QK transpose, QK transpose. So when I do this final matrix multiplication, I'll end up with an S by S matrix. And this first value here is going to be the product of Q1, K1. And then the second one's going to be Q1, K2. And the third one's going to be Q1, K3. And we'll just repeat this for all of the things. Now, what if we shuffled our order, right? What if we shuffled, before we did any of this, we just shuffled it? You'd still end up with it. Again, this is just dot product. So let's say we do, let's say we did 3, 1, 2. Right, so there you go, 3, 1, 2. So that means this is also going to be 3, 1, 2. This is going to be updated to 3, 1, 2. And then finally, we're going to have all this 3, 1, 2. 3, 1, 2. Which means this first row is going to be Q3, K3, right? Q3, K, oh, Q3, not QK. Q3, K3. Q3, K1, and then Q3, K2, right? That'll be it. isn't this the same numbers as before? Like if, okay, so for example, in the last row, before we did the shuffle, right? Before we did the shuffle, it would have been Q3, K1, Q3, K2, Q3, K3, right? Before we did the shuffle, this would have been the last row. But now, because we shuffled it, this Q3, K1 went here, this Q3, K2 went here, and this Q3, K3 went here. But remember, each of these things encode how is one word related to the other word. These, regardless of the order, how I've kind of, shifted these things around, Q3, K3, like both of these values, Q3, K3 here, when it's shuffled, or Q3, K3 here, before it was shuffled, are the exact same value. Just because they're in a different place in the matrix doesn't change the value. It's still the same dot product. It's the same everything. It's just changed locations because we've shuffled it, but the values are the same. And that means if our similarity metric is the same, regardless of the position of where these tokens lie, then our model is ignoring the fundamental positional information we need to encode our data. And this is a huge problem for transformers. Recurrent neural networks, like we've seen before, they implicitly have that information, right? Because we're for looping through all those tokens, one token at a time. So that information, just kind of through the inherent nature of the structure of a recurrent neural network, that positional information is already there inside the implicit bias. In the transformer, this is not true. Basically, we have the same information just shuffled around, but if it's the same information shuffled around, then that's a problem, because then the positional information is nowhere to be seen. And so this is why we need to add some type of a positional information, and that's what this stuff is, right? See, positional encoding. We have to add it both to the input English and the output French, but we need to add some positional encoding to it. And by default, they use a sine cosine embedding. So let's find, I think I went too far. Here we go, right? We're using the sine and cosine functions at different frequencies. So there's a couple things happening in this formula. First of all, the position is our time step. So we said that we will at most process 512 tokens, right? So that's our max sequence length. So our position will go from 0 to 511, right? There's our 512 tokens. The D model is the embedding dimension. How many tokens do I want to use to represent every single word? How many numbers do I want to use to represent every single word? And that's 512, like we said it, right? The embedding dim for our model is 512. And the I is along the embedding dimension. So let's kind of draw a quick schematic, because I think this is the hardest part of the implementation. So I want to give it a little bit extra love because it's super cool. And then we'll plot it afterwards. So again, data for our neural network will look like this, right? Sequence length by embedding. This is our data, right? It's going to have some sequence length. Now, I know that S has to be less than or equal to 512 because I've set that, right? And if you, again, take a look at the implementation of the data set and the data loader and all this stuff that we did last time, we ensure that anything longer than 512 gets cut, right? So we don't keep anything longer than 512. And then we have something like this. This is going to be our positional encoding. It's going to have the same embedding dimension, but this is going to go to 512, right? 512. So we have a matrix of values that's 512 long for the maximum sequence length we're willing to encode, with the same embedding dim. And when we go to do our embedding encoder, inject our embedding information, our positional information, we just add on up to the S. So if there's S here, so we're basically just going to slice off the portion that we need and add that to our data. And that will be us injecting positional information into the model. And now let's kind of talk about a couple of details. So this D model here would be our E, right? The dimension that we're using. So we're good to go there. The POS position is going to be 0 to 511, right? Basically position 0, position 1, position 2, so on and so forth. And this I is an index in our model itself. So or in the embedding dimension itself. So what I mean by that is, notice how every even position 2i gets a sine, and every odd position 2i plus 1 gets a cosine. So that would be, if we kind of, take one of these vectors and break it up. Let's say that's what it was. So we have position 1, 0, 1, 2, 3, 4. That means every even position is going to get a sinusoid, right? Basically the sine, it'll be the sine, so this first one, right, 0. This would be, let's just take this formula. The formula is sine the positional information divided by 10,000 to the power 2i over e in our case, right? So let's take a look, right? 2i over e. And so there it is. And so in this first positional information, we're in this first location in the matrix, it's going to be sine of, we're in position 0 right now. This is vectors, you know, the first position. It's going to be 0 divided by 10,000 to the power 2i. In this case, it's going to be, this is 0, so it's going to be 2 times 0 over e. And obviously this is just a simple, you know, if it's all in, actually in the first case, everything is 0 over, so it doesn't matter. So maybe it'll be more interesting to do a different example. But we're basically going to populate our even value embeddings with positional embeddings with this formula, right? Just plugging it in. And then for the odd ones, we're going to do exactly the same thing, but we're going to fill it with our cosine instead. So these are going to be, instead of sines, these are going to be cosines, right? Just following this formula directly. And so again, referring back to the formula, we just need to create a couple things. We need to create this 2i, vector. We need to create this position vector, and then we just compute the formula and we are done, right? So nothing too crazy. Let's go ahead and just implement it, and it probably just makes more sense by drawing it out or implementing it. So we're going to do class positional encoding nn.module definite self, and we're going to provide some information. The max len, how many tokens am I willing to go up to, and then the embed dim, right? How many embedding values do I want to represent every token? And then requires grad equals false. Do we want to train this positional embedding or not? In this original implementation, we won't do it. When we do the vision transformer next, we will do it. So for now, this should be good. So we're going to do super positional encoding self dot init, just like always. And we're going to just store some of these variables. Self.maxlen is maxlen. Self.embedDim is embedDim. And we're going to do self.requiresGrad is equal to requiresGrad, and shouldn't be underscore, should just be requiresGrad, just like that. And we're going to create our encoding. Self.encodings is equal to self.build positional encodings. We're gonna write a new function that does this. So def build positional encodings self, and we're just going to follow that formula directly. So the easiest way to do this is go ahead and just create a empty matrix. So torch dot zeros, and so like we saw, our positional encoding matrix is a sequence length by embedding dim matrix. So why don't we just populate it with zeros and then fill in as we actually build the matrix out? So torch.zeros, and it's going to be self.maxlen by self.embedDim, and we're going to make sure our D type is torch.float32. Right, we're going to make sure it's that type, a floating point precision matrix. Now that we have that, we can go ahead and create our position index. And this is going to be torch.arange from 0 to self.maxlen, right? And again, D type is equal to torch.float32. But we have one little annoyance here, position index. So let's go ahead and run this. Actually, to run it, we need to actually have it. So we're going to do if name equals main. We're going to do our positional encoding is our equal to positional encoding, and we're going to say the max len, I'm going to say it's 256 right now just to keep it different, and our embedding dim is 512. But this will be 512 and 512 later, just I want to have different numbers for the different dimensions so it's clear. So we can want to run python model.py. This is our positional encodings, right? So there we go. Or sorry, the position indexes, right? It goes from 0 to 255 because I specified that there's 256 total positions that I want. So there you go. The problem is that our position encoding matrix, the index, right, position is a column vector, 0, 1, 2. It goes along the column. We currently have a row vector, right? Basically just a single row. So we just need to do a quick reshape to make it a column vector. Dot reshape -1, 1, right? So we're going to add that extra dimension. And there we go. We now have a column vector of positions. And now that we have that, we're going to perform the rest. So the next step is we need our embed skip dim. So basically this is this variable right here. This 2i, we need to actually produce 2i, right? So 2i is just going to be a vector from 0 to our embed dim, but instead of going, 1 at a time, we're going to go 2 at a time. So it skips. So we're going to do position index or embed skip dim is again torch.arange 0 to, in this case, embed dim. But we're going to do step is 2, right? Step is 2. And we're going to do dtype is equal to torch.float32. And if we look at our print embed skip dim, there we go. This is a row vector. So notice this is a column because our position information goes down the column. This is a row because our embedding dimension goes across the rows, right? So that's all it is. And if we do position index times embed skip dim, this should produce a matrix, right? So this is how PyTorch will automatically broadcast and copy and do all the operations for us. If we look at the shape, any operation between these two will produce the produce what we need. So we should actually no, it won't produce exactly what we need, but let's just keep going and it'll make sense. So what we're going to do is let's just print out our embed skip dim to the power. Actually, no, this is exactly correct. The reason it's 256 by 256 is because it skips, right? We had an embed dim of 512, but we only have a number for every other one, right? So it goes 0, 2, 4, 8. So yeah, 256 by 256 makes sense. And basically, every even step of encodings will be filled with one version of this, the sine, and every odd step will be filled with a different version, the cosine. So yeah, no, it is correct. So we're good to go. Okay, so what we want to do is print, right, the embed skip dim divided by self dot embed dim, right? So we're going to just start following the formula. This is me dividing all the 2i's, 0, 2, 4, 8, whatever, divide by the embedding dimension. So that'll look like this. Right, I just took everything and divided by 512 in this case. And then the formula states that we want to do this to the power 10,000 to the power this, right? So let's do that. So we're going to do 10,000 to the power all of this stuff. So there we go. That will produce something like this, right? So we have all these numbers. Again, still a row vector. And then we want to do our position index divided by this. And this will produce our values, right? Before we do the sinusoid. So this will produce our values. And we want to just do torch.sine of this. And let's just print out the shape because the numbers are less interesting just for now. And it's a 256 by 256 matrix. And basically this is this part. So this is this one right here, and then this one right here, and then this one right here, and then dot, 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 right? We keep going. So it's basically every even one. So if we have 512 total, we have 256 even positions, right? So this is these are the 256 positions. And all we want to do is store in our encodings for all the rows and from 0 to the end, but in increments of 2, right? So this 0, : 2 will go from 0 to the end, but skipping, one at a time. So it'll be, every other one is going to be set to this. And we can print encodings. And we should see that every other one, let's go ahead and pick some smaller matrices. So let's do 16 and 8, whatever, right? Because it doesn't matter. I just want to make it more clear. we can see that every other position has been filled. So see, it's this one, then this one, then this one, then this one, then this one. So every other position has been filled with this sinusoid information. The first one is still all zeros because the sine of 0 is just 0. So there we go. We will do exactly the same thing, but now we're going to start at 1, go all the way to the end, because this is every other one starting at the odd value. So 1 to the end, and we're going to fill this with cosine instead. And so now we should see something like this. And note it goes 0, 1, 0, 1, 0, 1, because the cosine of 0 is 1. And then everything else gets populated. And that's it. This is our encodings matrix. That's basically it. Dot shape. It will be a matrix of our sequence length by embedding them, 8 by 16. Just as we had created it, we've just populated it with these values. Again, we could have done a learned positional encoding, right? And we'll again see it's actually much simpler than this. So we'll see that next time. I'm trying to make it, add different levels of complexity to every video. So this is probably the toughest thing we're implementing here today. Okay, good. So now that we have our positional information, you might be a little bit curious what this looks like. So we can actually do that. We're going to do import numpy as, or not numpy, matplotlib.py plot as plt. This is going to be a little bit dumb, but I'm just going to toss this in here, encodings. I wonder if this will work. I might have to convert it to a numpy array ahead of time, but let's see. And let's make this what we know it's going to be, 512 by 512. Is this going to work? Oh yeah, it does. Nice. So this is what that positional information looks like. You have this this stuff, right? So it's hard to kind of interpret this, but basically this is the positional information that we are adding for position 0, position 1, position 2, and the kind of these different scales of kind of these waves that you see here, going from 0 to 512, tells the model where things are, and it's effectively just a transform to go from one thing to the next to the next. This wouldn't be a very complicated thing for a neural network to learn. So there you go. These are our positional encodings that we are doing. The effect, why did they pick 10,000? So let's say we make it, let's just update this. So we're going to do this twice. Let's pick 100 instead of 10,000. What happens if we do 100 instead? And we're going to add this. So why pick 10,000? So we'll see the first one here, right? This is what we had just seen before. So there you go. And then we see this next one here and see how it goes out further, right? So the change is kind of happening over more of the embedding dimension. I'm sure there was somewhat of a hyperparameter tuning that they had to do, trying different numbers, seeing what works. But by reducing the denominator, right, by making the denominator smaller, you'd make the overall number bigger, which means it's a higher frequency. And maybe if the frequency is too high, the attenuation is too much and the model's not happy with it. So they picked a pretty low frequency here, right? 10,000 is much bigger denominator. So there we go. We have our encodings. And the last part is our encoding is going to be nn.parameter encoding. So we haven't seen nn.parameter. But when we do model.toDevice, right? When we move our model to the GPU, for example, only modules, like PyTorch modules, get pushed to the GPU, which is nice. But if we just have something called encodings here, this will not go to the GPU by default. You'd have to do it manually. By wrapping it in nn.parameter, we're just converting it to a parameter, and then PyTorch will treat this like a module that needs to go to the GPU. And this is also our opportunity to set the flag requires grad equals self.requires grad, which by default we have set to false, right? We don't want to update these positional information. We don't want to train it. We don't want to do anything. We just want to use them as is. So there we go. So I think that was probably the toughest part of our whole implementation. So that's great. So forward function, really easy. Forward self x. All we're going to do is grab our sequence length. Is going to be x.shape1, right? Because remember, it goes from batch, sequence, embedding dim. That's the shape of our tensor. So the 1 is our sequence length. And we're going to do encodings is equal to self.encodings. And we're just going to index up to the sequence length that we need. And this assumes that sequence length is less than 512, right? Or whatever the max is. So we're going to index it, and then we're going to do x equals x plus encodings, and then we return x. So this is me injecting positional information into my data. And this does exactly what I mentioned here. We index off the piece I need, and then we add it to x, and we are good to go. So that's our positional information done. On to the next piece, right? So let's look at the paper again. We need embedding matrices, right? So inputs are tokens, outputs are tokens. We need to convert these tokens to numbers, or embedded vectors, right? Vectors. We need to convert these tokens to vectors. And to do that, we need our embedding matrix. So these embedding matrices are identical to what we saw in our LSTM RNN exploration. We just conversion of tokens to numbers. So let's go ahead and produce this. This will be very simple. All we're going to do is class embeddings, right? And then dot module. And we're going to have two embeddings in here. So we're going to do def init self. And what I typically like to do is pass in the config. So I could have actually done this for the first one as well, because this information was there anyway. So let's actually do that to make it consistent. I'm going to pass in the config. This is basically the thing that I wrote above, config. And so that's going to be here. And so how these config files work, very quickly, it basically just produces a dictionary, nothing crazy. Let's just comment this out. We can do our config is this. We can also change values, like if I want the max source length to be something else, but by default, I just want to use all the default values that are already set. And there you go. This is your config, and we can access it like a dictionary, right? So there we go. So let's go ahead and set this to config.max source. Actually, you know what? Because we'll have positional encodings for both of these, we're not going to do that here. Let's just leave this one alone. You'll see why later. Yeah, let's go ahead and put this back how it was. So we passed in maxlen, embed dim requires grad. Yeah, let's just leave that alone for now, because we're going to be we have positional encodings for two things, so we're just going to leave that as is, and that is fine. Yeah. Okay, good. Yeah, let's just keep it simple. Let's just leave it as is. That's fine. Don't want to mess with the code too much when I know what works is already working. So self.config. Okay, so what we're going to do is super embeddings self.init, just like before. And we're going to do self.source embeddings is equal to nn.embedding. And this is going to take in our config.source vocab size, right? So this is how many possible tokens are there, right? What's my vocab size of my English by our embedding dim, right? Config.embedding dimension. How many numbers do I want to use to represent each of these things? And then similarly, we're going to have a second one. We're going to have a self.target embeddings. This is going to be for our French, nn.embedding. We're going to do config dot, I called these target vocab size. So there you go, target vocab size by config dot, again, embedding dimension. How many numbers do I want to use to represent each one of those French tokens? So we have two different embedding matrices here because we have two languages, right? We need one for English, one for French. So there you go. That's our pink modules. And so all we need to do is set it up. This is where I will define the rest of the information. We're going to do self.source positional encodings. This is what we just wrote above. This is going to be our positional encodings with config.max sourceLen, config.embedding dimension, and config.learn positional embed. So there you go. And then self.target positional encodings is equal to positional encodings, config.max target len, config.our embedding dimension, and config.our learn pause embed. Right, so there we go. So what I have is two embedding matrices to convert my English or convert my tokens to vectors. And then I have two positional matrices. So that's why I left it as is up here. I didn't pass in the config, so I could just call this module twice, once for each one. So I just have one embedding matrix that is everything. So I have my positional information for French, positional information for English, and I have the corresponding matrices. Now, technically, if my max source length is the same, which it is, so because I have the same max source length in both of them, I could have actually just reused one of these embedding matrices for the positions, right? I could have just used one positional encoding matrix. I didn't need both of them. But in case you wanted to have different ones, different lengths for both of them, then you'd need separate ones for the different lengths, right? So there we go. Now what we're going to do is, instead of writing a forward function, you don't actually have to write a forward. It's just a, it's just the default function that PyTorch will run. We'll just write two different functions: self input IDs. Oh, right. This is for our source. So our embeddings, we're going to be passing in tokens, right? So embeddings is equal to self.source embeddings input IDs. Right. So this is going to take my tokens, convert them to vectors, and then embeddings is equal to self.source positional encodings embeddings. And this is going to take my embeddings and inject that positional information into it. And we can return embeddings. And our target source, our forward target, will be exactly the same thing. It'll just be for the other one, TGT. So again, this is going to be for the target embeddings, and then it's going to be for our target positional encodings, but everything else is the same, right? Nothing changes. And so this has finally implemented just the start of the models, right? We have inputs, we embed them, add positional encodings. We have our French, embed them, add our positional encoding, and that's what exactly both of these chunks do. We have our inputs, embed them, add our positional encoding. And so we're good to go, right? This is our embeddings, very simple. Now for attention. So I'm going to go through this much faster than the last video. So we spent, I don't know, close to like a couple hours, I think, on attention, maybe like two or 3 hours, like going into the really nitty-gritty details of everything you need to know about attention and all the implementations. And this implementation I'm about to do is the final implementation that we do in that video. I'll give the high level idea here, but if you really need the details or you didn't see the video, again, just please go watch that video. I don't want to make every video too much of a repetition of what I've already talked about. So self, we will pass in our config, super attention self dot init, just like always, and we're going to do self dot config equals config. This is just so we can access this config information in other parts of the model. So there we go. And we need to make sure, right? So we're going to be doing multi-headed attention, not just one. So we need to ensure that our config.embedding dimension is divisible by our config.num attention heads, right? And otherwise we need to do double check that embed dim is divisible by heads. There we go. And so our self.headDim, right, head dimension is going to be config.embedding dimension divided by config.num attention heads. There we go. Right, so that's what we're going to do. And so now we're going to just set up our three matrices, QKV, and our output projection. So self.qproj is equal to nn.linear. And it's going to be between the config.embedding dimension, right? We're going to go from embedding dimension to config.embedding dimension. And this is because we will be doing the efficient attention, you know, doing all the parallelizing across the batch and the heads and all that stuff within the tensor rather than for looping. So we're just going to, you know, set it up like this and then cut it up after the fact. And then we'll need actually 4 of these. Oh, let's fix that. So we're going to have a qproj, kproj, and we're going to have a vproj. And then we're going to have an output proj, right? That'll be the final projection. That'll get all the heads to, get to know each other. So that's our setup, all the matrices that we need. And so now we're going to write our forward function. And our forward function is a little bit more complicated than normal because we have a couple things that we need to consider. So we can pass in a source, right? The source is, if we only pass in the source, we're doing self-attention. If we pass in a source and a target, or sorry, let me fix that again. If we pass in the source, we're either doing self-attention or causal self-attention. Those are the two options, and we'll have a flag that will deal with that in just a second. If we pass in a source and a target, then we are doing cross-attention between the source and target. And so we can then pass in our attention mask equals none by default. We don't need it. We will for training, but we really won't need it for inferencing. And then causal is false by default. So there we go. Again, so we want to accommodate for all the variants of attention we're going to deal with just in one class to keep it simple. You could also write 3 different ones, but I wanted to just make everything as self-contained as possible. So we're going to do batch, source len, and embed dim. So by default, right, all we will have is the source, right? If we're not doing cross-attention, then all we have is the source. So we do if target is none, right? If we don't have the target, then q is equal to self.qproj source, right? We're going to pass that in. And remember again, this is going to produce a, this operation will produce a batch by sequence by embedding dim. But we want to cut up this embedding dimension into the different heads of attention that we want. So we can do dot reshape, and we're going to cut it up. We're going to leave the batch alone. We're going to leave the source len alone. But we want to split our embedding dim into self.config.num attention heads and self.headDim. So this will take our E and cut it up into H by headDim. I'll call it HD, right? So number of heads by headDim. But we want to parallelize on the head and batch dimension every attention computation, which is between the sequence and the headDim, right? Between everything. So we need to put the head dimension at the beginning. So we need to permute and flip these two dimensions around. We can permute it, we can transpose it, we can do whatever we want. We can do dot transpose 1, 2. So that'll flip S and H, and that'll produce a H by S. And then I can go ahead and repeat this operation for Q, K, and V, right? So Q, the K will be identical, except we're going to be using kproj in this case. And then the V will be identical, but we'll be using the vproj in this case, all producing this thing. And so when we do the matrix multiplication, like QK transpose, it's going to be between a Q times H times S times HD times a Q times H times, we're going to transpose this, so it'll be HD times S. And this will produce basically a S by S matrix, just like our regular self-attention, for each sample and for each head independently. So all the heads are being computed independently, which is why we're just spending this extra effort doing all this matrix manipulation. So there we go. Again, just look at my other video for more details. This is just the crash course in what's going on. Next thing we need to deal with is if attention mask is not none, right? Different English samples can be of different lengths. So we have some padding, and we want to make sure we don't attend to those padding values. So by default, the flash attention mechanism that we are going to be using leverages a Boolean attention mask. So we're going to just make sure attention mask is equal to attention mask.bool. It's already a Boolean because we already implemented it that way, but that's what we're doing. Now the thing is that our attention mask is going to be batched by sequence, identifying which of these time steps in the sequence do we want to compute attention for, and which ones do we not want to compute attention for. Our attention matrix, when we actually compute it, it's going to be batch by heads by sequence in this case. So we just need to add some extra dummy dimensions there just to make it match, right? So we're going to first add that. So attention mask is equal to attention mask dot unsqueeze squeeze 1 dot unsqueeze 1, right? So that's going to add these two dummy dimensions in our attention mask. But the flash attention that we're using, the scale dot product attention that we're using, expects a batch by 1 by S attention mask. So it will broadcast over the head dimension, that's fine. It will not broadcast over the sequence dimension. So in this situation, we just need to repeat 1. So we don't want to repeat the batch dimension. We want to leave this one alone. We want to repeat this one here S number of times, and in our case, S is our source len. And then we want to leave the last one alone. And that will get this to a batch by 1 by S by S. Again, what this looks like, I go into way more detail in the other video. Now that that's ready, we can go ahead and delete all this. Okay. And we can do our attention computation. We can do attention out is equal to f.scale.product attention. So this is flash attention already built into PyTorch. You could get faster flash attention or newer variants using like the original DAO Labs implementation, their GitHub, but I don't want to add any extra installs or imports, so this is going to use the PyTorch one, and I've never had an issue with it. So we're going to provide a QKB. We're going to provide it the attention mask is equal to our attention mask that we produced. If attention mask is none, right, then we never would have done this, and then this would just be none, right? So that's how it is. Our dropout p is going to be self.config.attention dropout p, but we're only going to do this if self.train, or is it training? Let me double check. Training, yeah, training. Else 0.0. So self.training, we never defined it. It actually comes from nn.module. So when we do like model.train or train, and then model.eval, right? When we're doing this toggle for training versus inferencing, it's actually toggling this flag internally, the self.training flag. And so if we're in training mode, then we want to use a dropout. And if we're not in training mode, we're in evaluation mode, we don't want any dropout. So that'll be 0. So there we go. That is us computing attention. And that basically covers the self-attention. Actually, no, one more. There's also is causal equals causal, right? Are we doing a causal attention or not? So are we doing a decoder attention where we don't want the past to look at the future? Or are we doing an encoder attention where we can look both directions? So this is our self-attention with both a causal or non-causal flag. Great. Next, if we have a target as well, right? So now we're doing cross attention. We can do target len is equal to target.shape1. The batch and the embed dim in this case is set to the same thing, so I'm not going to worry about it, but you could make it more general. Like what if you had different embedding dimensions for the source versus the target? I'm not worried about that right now because we don't need those extra layers. So there we go. Target len, that's what it is. And everything else is almost identical. Remember, the cross attention and self attention are the same. The only difference is that we want our queries to be the thing that we want to produce. So French, in this case, our French will be the target, the thing we want. And our source will be the English, the thing we want to weight against, of how are our French tokens related to our English tokens. So there we go. We have gone ahead and done that, but we need to make sure that for the Q, we'll use the target len, but for the K and V, which is based on the source, we'll use the source len. But everything else stays the same. This also means our attention mask, the attention mask in this case, will be for the English. We don't want our French tokens to attend to English padding tokens. So that's an important distinction, right? That will come up again later. So there we go. So let's do if attention mask. Again, if we have an attention mask is not none, then we're going to do attention. Actually, everything here is going to be identical. But in this case, our attention implementation, the final attention matrix, is going to be batch by heads by source len, by target len by source len. How is every single word in the French related to every single word in the English, right? So target len by source len. And the thing is that once we have this, so everything else stays the same, But instead of repeating source len number of times, we want to repeat target len number of times. And that produces the attention mask that we need for our computation. And then this attention out will be exactly the same. Right, so we can just add that in. Attention out is that. It's going to be, again, between QKV. We may have an attention mask during training. During inference, we won't, but during training, we will. So there we go. We have that. And that's it. And the important part is these attention implementations for cross attention can never be causal, right? It doesn't make sense to have a causal attention here. So there we go. And lastly, attention out is equal to attention out dot transpose. We're going to basically put it back. So again, we're currently in a batch by heads by sequence length by head dimension, right? That's what we're in. So we need to transpose these two things again, and then flatten head and head dimension to go back to our original shape. So we transpose these two, so that'll be S by H is what we flipped. And then we want to just put these back together to produce H times head dimension, which was just our embedding dimension. So we're going to do dot flatten after the second dimension, right? So there we go. And then lastly, what we just did is multi-head attention, where different heads learned different types of information about the data, about the specific sentence. But the heads haven't talked to each other, right? We need an opportunity for the heads to speak to each other. So that's the attention out is equal to self dot out proj attention out, and we can return attention out. So there we go. So we're going to give this a quick test to make sure this works. But again, if you need additional details of exactly what happened here, I had a whole video digging into basically anything and everything you would care about for kind of this vanilla attention implementation. So let's go ahead and test this out. We're going to do attention. Let's do attention is that. And we're going to provide it a config. So the config will be transformer config. Everything else stays the same, right? So I know that, and let's give it the config. Let's just do self-attention for now. We're going to do data is equal to torch.rand. And I'm going to have some batch size. So let's say a batch size of 2 by some sequence length of 35. And so I know the embedding dimension is 512, right? So there we go. And so we just want to do attention, data, and that's it. So we want to print this out. So this would be self-attention with causal mask as false. Let's see if it works. Looks like we have a bug. So we have 512. Let's quickly check here. This is why we check. We can do print. Okay, let's just check here. So for here, we had a 512 embedding dim, and num attention is 8. Is that not what we had here? Embedding dim by num attention is 8. Let's see, double check. Oh, we need to do, make sure it's 0, right? There we go. You didn't have an actual conditional in there. Okay, next. Oh, we don't need you. Okay, next, forward missing one positional argument. So by default, our target should be false. So let's set that to false. Now our bool has no, target.shape. Why is it going into target? If target, oh, sorry, this should be target is none, not false. There we go. Always the little things. There we go, right? Produces the input shape and the output shape are identical, right, in a transformer. So there you go. We have our input and output in this attention computation. Let's say we have our data 2, which is torch.ran 2 by 61 by 512, right? And actually, let's make it more clear. Let's make sure, let's say this is the English and this is the French. So what we're going to do is our source is the thing we want to weight against. That'll be English. And our target is the thing we want. That'll be French. And so now we can take a look and see. Let's see if there's any bugs here. Notice the output shape, 2 by 61 by 512, matches the French, because the French is what we want. All we want is a weighted average of how is the French related to every English token, not the other way around. So in our cross attention, we're going to provide the French to the target. And during self-attention, if we're doing self-attention on English, then the source is English. And if we're doing self-attention with the causal mask on French, then we're going to do sources French. So there we go. We now have our attention implementation. That's good. Next up, feed forward. This is the easiest part of the whole model. So let's take a quick look here. Let's see, here we go. So the feed forward network is basically just a weight matrix with a ReLU and then another weight matrix. So it's just a stack of two different weight matrices. And it says the D model is 512 and the inner layer has a dimensionality of 2048. So that's a 4x, right? That's a 4 times upsampling of this. And this is why we have this. MLP ratio controls that upsampling. What do we send the embedding dimension to in the hidden dimension? So we go from 512 to 2048, and then we go back down to 512 again in the last one. Good. So implementing this is very simple. Now we actually aren't going to be using a ReLU function. The Gaussian linear unit function actually works a lot better. Let me show what that looks like. So GLU function. We're using GLU, right? Yeah, we are using GLU. So GLU has kind of become kind of tested as a slightly better function for this stuff. And this is what GLU looks like. It basically looks like ReLU, it just has this slight dip in it. It allows for activation, like some activation information or gradient information in values close to 0. Otherwise, it can lead to like vanishing gradient problems and stuff like that. So it helps, right? It gives some help in these lower values that we're dealing with. Okay, so let's go ahead and X out. Okay, good. So we'll be using GLU, but other than that, nothing else is changing. So feed forward, again, nn.module, just like before. Def, init, self, config, and just like before, super feed forward self dot init. Okay, so first of all, the hidden size. So what is, okay, so maybe let's go ahead and do this. So we have 2 linear layers, but we have a hidden size in the middle, and that hidden size is just going to be our config dot embedding dimension times config dot MLP ratio. So what are we expanding to? So if we have 512 and it's 4, then it goes to 2048. Right, so that's your expansion factor. So our self dot intermediate dense is what I'll call it, is nn dot linear. It's going to go from config dot embedding dimension to our hidden size, right? And then our self dot activation is going to be nn dot GLU, right? The GLU activation function. And then we will also have a dropout here. Self dot intermediate dropout is nn dot dropout, and the dropout will take a config dot hidden dropout p, right? So, you know, to help with overfitting and stuff like that. Similarly, we're going to have a self dot output dense, right? This is our second linear layer. The second linear layer is going to take in our hidden size and output our config dot embedding dimension. So as you can imagine, basically we have one linear layer going from 512 to 2048, and then the second one's going to go from 2048 down back to 512, and that's it. So that's our output dense. And then our self dot, again, output dropout is going to be nn dot dropout, and it's going to be config dot hidden dropout p, which will all be 0 by default, right? So there we go. And then def forward self x, right? And all very simple, just a couple linear layers. This isn't any different from the very first PyTorch video I made. All we want to do is pass into our intermediate dense, our x. X is then going to be self dot activation. Actually, maybe it'll be good to just make sure we look at the tensors as we're going. So we're going to call this feed forward. Let's call this ff. Let's say our rand is equal to torch.randn. We're going to do a batch size of 2. by 32, let's say a sequence on 32, and we know our embedding dim is 512. So we're going to pass into our feed forward our rand. And so if we print the x.shape after the feed forward, nope, went too far, we will see a 3 by 2 by 2048. So we took a 512 embedding dimension and projected it up to a 2048. And then at this higher dimension, we are going to do x equals self.activation x, and then x equals self.intermediate drop x, right? Drop out. So there we go, right? Nothing changed. We just added an activation function. And then finally, we're going to do x is equal to self.output dense x, and then x is equal to self.output drop x. And we can then return x, but let's print the x.shape here real quick. We are back to 512, right? So we go up to 2048, do our activation at the higher dimension, and then project back down to 512, and we are good to go. So a lot of your weights, right? A lot of the parameters of your neural network are actually inside these feed forward modules. This is why alternative methods have been proposed, like mixture of experts and things like that, which we will be implementing in a future video, but for now we are staying simple. We have now, okay, it's always good to just refer back to our picture, right? We have now implemented the multi-head attention, mass multi-head attention, and this cross attention. We've also implemented these two feed-forward modules. Now it's time to just kind of wrap them together in these transformer blocks and include this add and norm thing. And we'll see what that is in a second, but you should already start thinking, I take an input, I create a copy, I pass it through a network, and then add it through. That looks like a residual connection, because it is. This is the same residual connection that we have in ResNet models. So there we go. We're going to write two different things. We're going to have first class transformer former encoder, nn.module def init self, pass in the config, self, and then super transformer encoder self dot init. There we go. And so we're going to do, let's check, an encoder, this left side here, has a attention module and a feed forward module, and this add and norm between it. So we're going to do exactly that. Self.encoder attention is equal to our attention config, right? We're just going to pass in our, it's just our attention, right? Nothing fancy. And whether or not it's a self attention or cross attention or causal attention is controlled by our forward function when we actually pass in the data, and you will see that in just a second. So we have our attention. Then we have a self.dropout, just like always. We're going to have a nn.dropout. I'm going to call this config.hidden dropout p, right? What dropout probability we want to do in all of our layers. And then self.layer norm. And this is a crucial thing that we actually have not talked about yet. So let's go ahead and briefly discuss it. Layer norm. I think there's a really great picture for this. Here we go. Papers with code is great. So here we go. We have something known as batch norm and layer norm. And notice the crucial difference here. In batch norm, we are averaging along the batch size, n, our number of samples. In layer norm, we're averaging across, or not averaging, but standardizing, right, mean and standard deviation, across the channels. And the important thing here is that transformer models are very expensive. They require lots of compute. And we talked about accelerate, right, training on multiple GPUs, that sort of stuff. But even with that, we can only fit such a large batch size. And if we don't have large batch sizes, you wouldn't feel confident about your the statistics you calculate on, right? Mean and standard deviation only makes sense when you have a sufficient batch size. And so calculating an average across a batch size when our batch size is not large because we can't fit it on the GPU is not a good idea, which is why we prefer layer norm. Notice the computation does not occur on the batch, but happens per sample. It's a per sample operation. So there's no cross batch computation happening. So that's one importance of layer norm over batch norm. The other thing is batch norm becomes expensive when we are doing multiple GPUs, because you can imagine, let's say you want to do a batch size of 1024, right? So you have a batch size of 1024, but you can't fit 1024 on one GPU. It's too big. So now you're training on, let's say, 256 GPUs, and you have a batch size of 1024, which means each GPU has a batch size of 2. Like each of them are processing 2 samples at a time. Which means when we want to compute our statistics of the mean and standard deviation across all 1024, all of the GPUs need to synchronize and talk to each other to kind of come up with, oh, what means did you get? What standard deviations did you get? And then accumulate that information across all of the samples. And that inter-GPU communication is always one of the slowest parts of neural network training. So we want to avoid that as much as possible. So why not just do a per sample normalization? It's not as robust, it's not as good, but it's good enough and it seems to work really well for transformers. So we will be basically using layer norm for the foreseeable future. We'll be looking at some other methods, group norm and instance norm, when we start looking at some of the GAN implementations or the diffusion implementations. For now, we're just going to stick with layer norm because that's what they use. So let's go ahead and do that. So our layer norm, it works exactly the same. nn dot layer norm. And all we need to provide it is we're averaging across the channels. So how many channels, or the embedding dim in our case. What's the embedding dim? It's going to be our dot embedding dimension, right? That's what we have. Up next, we have our feed forward. So self.feed forward is equal to nn dot, not nn, it's just going to be our feed forward module with the config, just like before. And then self.final layer norm is going to be nn, again, another layer norm. Again, config.hidden dropout p. And there we go. This should look like basically this is the first norm. So one norm is after attention, and the second norm is after the feed forward. But now we have to do the adding as well. So let's go ahead and do that. So we're going to do def forward. In the case of an encoder attention, we will only have self x, right, our input, and an attention mask equals none, right? Because this is this is never causal, right? There's no causal mask here. We can look both directions, and that's it, right? There's nothing else. We're going to have all the other stuff, all this extra stuff we implemented for the attention, target, attention mask, all this stuff will happen in the transformer decoder, but we're not there yet. So all we need right now is the data and my padding mask, and that's it. So let's go ahead and create an example. So we're going to do transformer encoder. So I'm going to call this T. And my data is my data. That's fine. And I'm not going to include a attention mask, but just assume it's there. Otherwise, it'd be a little bit annoying to generate it right now. So we're going to do, first, we need to take x and pass it into attention. So we're going to do self.enc attention. We're going to pass in x with our attention mask is our attention mask. So that's me passing my data in. And after we do that, we want to apply dropout to it, right, to help avoid overfitting. Self.dropout. Self.dropout. We're going to apply our dropout to this. And finally, our residual connection. We're going to do x equals x plus this. Now, the really nice part about transformers is the input shape is always the same as the output shape. So when I do x equals x plus something, I don't have to worry about, misshapes and stuff like that. If you remember in ResNet, because of the convolution downsampling and stuff like that, the output shape could be different from the input, and we had to do a little bit of extra work with those identity convolutions to ensure the shapes lined up. Transformers make it very simple. We don't have to do any of that here. So we have this. Next, we're going to do x equals self.layer norm x, right? So this is our data, add and norm, right? So we went ahead and normalized it, or added it, residual connection, and then normalized it, and we are good to go. And again, we're going to do x equals self dot feed forward x, and then x equals self dot final layer norm x, return x, right? So again, we take our added and normal residual connection, give it to the feed forward module, and again, add a norm. So there you go. We have to do, oh, forgot that, x equals x plus, right? Add, and then norm. And there we go. This is our transformer encoder. Nothing crazy, nothing too complicated. So we are good to go there. Next up, our decoder, transformer decoder. And as you can imagine, it'll look very similar to what we just did, just with the cross attention added in as well. So we're going to do def init self config super transformer decoder self.init. So what does our decoder have? It has a causal attention, add a norm. It has a cross attention, add a norm, and then a feed forward, add a norm. So we have 3 blocks happening here. So let's go ahead and do it. We're going to have first self.decoder attention is equal to just, again, attention with our config. How we handle encoder versus decoder versus cross is just handled through these in the forward function, right? A little bit later. So we have our decoder attention. We have self.decoder attention dropout. So drop is nn.dropout. And it's going to be config.hidden dropout p. And then we have our self.decoder attention layer norm, right? Layer normalization, nn.layer norm, and config.embedding dimension. And there we go, right? That's our first block. We have our attention, causal attention. We have to norm, and I just threw a dropout in there for good measure. And the next block will look exactly like this, except now, instead of decoder attention, we're doing cross attention, right? So again, cross attention, we will control it in the forward function, so we don't have to worry about it right now. We'll have a cross attention drop, and then we will have a cross attention layer norm, right? Because again, we have to do an add and norm, so we need another norm. And then finally, we have our feed forward. So let's just add that in. That will look exactly like this, self.feedForward. And there we go, right? There's our feed forward. Nothing again changed. Everything is good to go. And we can add in, it looks like I didn't actually add a, yeah, there's no, oh, my bad, I made a mistake here. So this is a layer norm. This should be config.embedding dimension. My bad. There we go. Config.embedding dimension. All right. And then similarly, this should be config.embedding dimension. All right, yeah, there we go. That fixes it. And now all we need to do is pass our data through. So this is where we're going to have more stuff. We're going to have self, we're going to have our source, we're going to have our target, we're going to have our source mask equals none. We're going to have a target mask equals none. And that's it, right? So this will, because this is the decoder, right? The decoder needs both this source information, or yeah, the source information, right? The source that'll be used for cross, and we need the target information, right? The stuff coming in. Which means we first need to do self and causal attention on the target. Then we do cross attention between that and our source input. And then we do the feed forward on that final output. So that's the step. So let's go ahead and do it step by step. So target is equal to target plus self.decoder attention drop. We're going to do a dropout on self.decoder attention. And this is going to be target. Our attention mask is going to be our target mask in this case, right? The attention mask for the French specifically, and causal equals true, right? We have a causal mask that we now place on this because this is a generative model, right? This is our decoder. So future time steps can only look at the past. We can't look into the future. So we add in that causal mask. So there we go. Actually, this might be a good opportunity to give a little bit more details about why we do the causal mask. I mean, you understand intuitively why, because we've talked about it, but just more practically why. There is another way we could have done our transformer implementation. For example, we could for loop through like pass in French token 1. Let's do a different color. It's brighter. We could pass in French token 1 and ask the transformer to predict French 2. And then we can take French 1, French 2, and ask it to predict French 3. And then we can take French 1, French 2, French 3, ask it to predict French 4, ... Like we could do this, and we actually will do this for the purposes of inferencing, right? But this requires a for loop, right? For loop. So for loops are expensive, and the question is, can we parallelize this in some way? Well, yeah, of course we can. That's what the causal mask is for. Because in the end, our attention output, right? Like we'll have attention, let's say we have F1, F2, F3, F1, F2, F3. It'll look kind of like this, kind of like this. And so F1 can only look at F1, and F2 can look at F1 and F2, and F3 can look at everything, right? F3 can look at everything. Which means we ignore this, this, and this, right? We don't compute these. This means when we multiply this by V, right? Because we still have to multiply, this is QK transpose, right? QK transpose. When we multiply by V, our outputs are embeddings, right? Embeddings of how a token is related to previous tokens, right? The relation between a token and its past, which means this token here for F1, the first time step, will only contain F1 information because it couldn't look at anything else. The second token can look at F1 and F2, but it can't look at anything else, right? Because it can't look forward. It can only look at the past. And then the third one can look at F1, F2, and F3 because it has all of them. And the key thing is using this F1 token, or the token that represents basically just F1, I want to predict F2. Using this embedding that represents a mixture of F1 and F2, I want to predict F3. Using a mixture of F1, F2, F3, I want to predict F4 if there was an F4, dot, dot, dot. And this F1 predicting F2 is this. F1 and 2 predicting F3 is this. F1, 2, and 3 predicting F4 is this. So it's the exact same operation as doing this for loop, just without doing the for loop, right? So that's practically why we do this causal mask. You don't technically need to. We could have just done it with the for loop, but who wants to do for loops when you can use nice GPU parallelism? So there we go. We have our target. And now we're going to do target is equal to self.decoder attention layer norm, right? Layer norm. We're going to normalize our target. And so this is the first chunk, right? We're going to do attention. This is causal attention, add in norm, just like before. So this is causal attention. Causal is true. Add in norm. And again, it will enforce causal because we pass causal in here. And we tell flash attention that I want a causal attention model. So there we go. And actually, to be on the safe side, we can put here, let's see. This will always be causal equals false, right? In the encoder, it's always false, so we can just put that in there to make sure it's always false. There we go. So causal is true. We do our layer norm. Up next, we now need to do the cross attention between the source information, the output of the encoder model, and our target. And how we kind of align this stuff and like set it up, we'll see in a bit. But for now, let's just pretend that this source right here is the output of this transformer model, right? So that's the output source. So let's go ahead and do that. Our target is now going to be target plus, because we have to do the add-in norm once again. Target plus self dot cross attention drop, self dot cross attention, and the cross attention is going to be between our source from the English, our target, the thing we actually want, the French. And so actually one thing to keep in mind, in this case, in this one up here, source is equal to the target because we are computing attention on the target on itself. So that, it is just, how you look at it. But here, technically, source is target. Here, source is equal to source. Target is equal to target. I could have probably done better about naming this stuff, but you should get the idea, right? Because we're computing attention on target to itself. It's just source because just passing in the source information, right, without a target will trigger a self-attention with, in this case, a causal mask. So, it's just how you write it. You could probably be clearer, but this should be fine. Okay, so we pass in a source, we pass in a target, and the important part is when we do cross attention, we don't want our French targets to attend to the source padding, the English padding. So we're going to pass in the source mask in this case. And then target is equal to target dot, is equal to self dot cross attention layer norm target. And there we go. Now we have this done. we've done our cross attention, we've add and layer norm. There we go. And then the last part is the same again. We just have a feed forward layer with one more residual connection. So we're going to do that here. But this is going to be target, TGT, is our target plus feed forward of our target. And then we want to normalize our target once again. And we can return target. And that's it, right? That's basically it. So again, let's recap here. The first part of our attention is this causal mask of how is the French related to previous tokens, and we use the causal mask to basically batch this operation so we don't have to do a for loop through it. The next question, what the second part asks, is how is all of the French related to all of my English? Right? How is all my French related to all of the English? And there's no causal mask here. So during inference time, right, we will be generating one French token at a time. Like, what's the next French token? What's the next French token? That's saying, given French 1, what's French 2? French 1 and 2, French 3. Or we'll be generating one token at a time during inferencing. And so cross-attention will say, how is French 1 related to all the English? And it will use the English information and French 1 to generate French 2. How is French 1 and 2 related to all the English? And that will generate French 3. How's French 1, 2, and 3 related to all the English? And that will generate French 4. And I hope you understand that pattern. That's basically what we're trying to do here. We'll be generating one sample at a time, one token at a time, and there we go. Right? So we have all the pieces placed together. And so now it's finally time to put together our transformer, like the final transformer, the model we will be using to train. Transformer nn.module def init self config, just like always, self config. I like these configs, it just, simplifies everything. So there we go, transformer self.init. Right, there we go. Good, so self.config equals config, right, just like always. And self.encodings is equal to our embeddings config, right? So these are all the embeddings, our token to vector embeddings, or the thing that converts numbers to vectors. And then we also have our positional embeddings in here. So all that information exists inside this thing. And now is actually a good time to go ahead and create some fake tensors so we can start testing our model. Transformer, right? So we're going to do our transformer. And we're going to have, let's say, English embeddings. Let's say it's that. And we're going to have, actually it won't be embeddings, it'll be tokens, right? So we're going to do English is equal to torch.randint, randint. We're going to generate some random integers. Let's say low is 0 and high is 1000. We can go up to, any number more than 30,522 will cause an issue. We're just testing right now. So we're just going to do from 0 to 1000. And we're going to do size is equal to we're going to do a batch size of 2. And let's say we do a sequence length of 32, right? Whatever it may be. So print English. Let's get rid of you. Okay, looks like I have a mistake. Can't access encoding where it's not available. Let's double check our implementation here because this should be encodings. There we go, plural. There we go. So I've just generated some random tokens, for my French or English in this case. And then similarly, I'm going to generate some random tokens for my French. And just to make sure it's correct, we're going to add a, I don't know, let's make this size 48. Right? So our French is of different length than the English because that's probably how it will be in most situations. And so we can pass into our model. Actually, we'll see that in a bit. Let's just kind of piece some of this stuff together and then we'll start testing these tensors just to make sure everything passes through. So we have our embeddings. One good way to test this is we can print out our model. And we should see that we have our source embeddings, target embeddings, and we have our source positional encodings and target positional encodings. Right? So there we go. All of this stuff in our embeddings matrix. What do we need next? We need self.encoder is equal to nn.module list. So again, we have to do n encoding steps, right? We have to repeat this whole thing n times. which means why not just make a list? And again, it's the same transformer block, just stacked on top of each other n times. So if it's just the same thing over and over again, then why not go ahead and just stack them ourselves, right? So we're going to create a list of these blocks. It's going to be transformer encoder, right? Transformer encoder config for blank in range config dot encoder depth. So how many do we want? That's how many we want. And so now if we print our model out, you should see all this show up. We have 6 transformer encoders, and each transformer encoder has an attention module, and it has a dropout and a layer norm, and this feed forward, and this final layer norm. So there's our encoder. Similarly, self.decoder is nn.module list. And we're going to do, in this case, transformer decoder, again, give it the config, fig, config, for blank in range, config dot decoder depth. How many of the decoders do we want? And so now if we print our model out, we should see the decoder show up as well. And the decoders are exactly what you think. We have we have 6 decoders, just like I said. We have a decoder attention with QKV, whatever. We have a dropout and that. We have a cross attention. Then we have the cross attention stuff. And then we again have the feed forward, right? So there's our entire decoder. So as you can see, very simple. You obviously would not want to define every single layer manually. It's just nice to have a, quick loop that puts this all together. So there we go. We have our full model almost set up. Last up, we need a self.head, right? This will be the prediction head. And so again, remember, how does prediction work? Let's say we're doing next token prediction, right? So we have French 1, French 2, French 3, French 4, ... That's our input. So using French 1, we want to predict French 2. And using French 2, we want to predict French 3, ... But what are my options? French 1 can predict, will actually output a vector, right? We'll output a vector of length. In our case there, we had 32,000 possibilities, right? This is token 1, token 2, token 3, ... token 32,000, right? So there's 32,000 possibilities of what French 1 can predict. We hope it predicts the correct one, right? So really, we will convert this to a probability vector, right? What's the probability it's token 1? What's the probability it's token 2, ... What's the probability it's token 32,000, right? What's the probability of each of these? And then we'll obviously go ahead and just max it, right? We'll take the max. We'll take the thing with the highest probability is what we want. So our head, right? Remember, each of these embeddings, right? Each of these embeddings are of length 512. So it's going to be a, the output embedding will be a 1 by 512, right? And we want to predict our 32,000 possibilities. So we need a linear layer that takes 512 things in and 32,000 things on the other end, right? So if there's any questions about this, you can go take a look at the RNNs or LSTMs for generation, where we wrote something that could actually generate Harry Potter text. We basically do exactly the same thing there, but we just need a linear layer to project to our possibilities. And we'll see what that looks like practically in just a second. But all we need here is an nn.linear layer. We're going to go from our config.embedding dimension to our config.target vocab size, right? So there we go. And our target vocab size again is French. We're doing French with 32,000 tokens. So that's our final model. And now we write our forward function. And in our forward, we have to pass in everything. We'll have a self. We'll have source IDs, right? That's our English. We'll have our target IDs. That's the thing we want to map to, our French. We have our source attention mask, which by default is none if we don't have it. And our target attention mask, which again by default is none. So step 1, right? Let's take a look at the model. And then we'll start passing tensors through just so we can see. Step 1 is we need to take both of these information, pieces of information, encode them with our embedding matrix, and then add our positional information. Okay, let's go ahead and do that. So that will be this module that we wrote earlier, right? For the source, we'll use the forward source, and then for the target, we'll use a forward target, which embeds them and adds the positional information. So there we go. So our source embeddings is equal to self.encodings.forward source, right? Specifically the forward source on our source IDs. And then our target embeddings is equal to self.encodings.forward target, again, target IDs. There we go. And now's a good time to start testing our model. So what we're going to do is T, and we're going to pass in English and French. And I'm not doing any attention masks, but assume they're there, right? Like they would be there if they were there. So print source.shape or source embeddings.shape target embeddings.shape, right? Let's see what everything looks like. They should be correct. Okay, it looks like we have a bug. So did you mean forward? Oh, looks like I spelled forward wrong. So let's fix that. Forward source, forward target. There we go. See now? All right, so there we go. So we passed in a 2x32. We outputted a 2x32 embedded with a 512 dimension. And for French, we passed in a 2x48. So we have a 2x48, again, embedded with its own 512, length vectors. There we go. That's our source and target embeddings. Now, step one is we pass our source into our model, right? Into our encoder, n number of times. So let's go ahead and do that. So we first repeat this whole thing n times. And only the output of the encoder, only the final layer, is passed to the decoder. So let's do that. So we're going to do for layer in self.encoder, right? So self.encoder is a list of layers. So we're just, looping through the layers, nothing fancy. We're going to do source embeddings is equal to layer source embeddings and source attention mask. So we're passing in embeddings into our model and then replacing the variable. So we're just basically looping the variable over and over again, updating our source embeddings. So at the end, we'll get the source embeddings for the final layer. After that, we need to do our decoder, right? So to the decoder, we provided our French input and our source, our learnt source embeddings at the same time. So we have to do both of them. So let's do that. So we can do for layer in self.decoder. We'll do target embeddings is equal to layer source embeddings, target embeddings, source attention mask, target attention mask. And there we go. So key idea, in every single one of these decoder blocks, right? We have 6 of them. They all get the same source embedding from the English, right? So same source embedding. So we just pass them in and there we go, right? We just pass them in and we just repeat it 6 times. And so there we go. We pass in our source, target, source embeddings, source attention mask, target attention mask. And again, if we look at our decoder, that's exactly what we want, right? We passed in a source, target. The target is the thing we want. The source is our context. And we just pass it through all this. So let's see if this works now. This will be the main test. And what I want to do is print out at the end, target embeddings dot shape. So you probably might, oh, wow, look at that. Not even a bug. Well, we'll find out later if it trains, but should be fine. So we passed in a 2x4, we embedded it to 512, and we've now outputted a 2x48 by 512, right? Just like that. And now that we have all this, right, what we've outputted is this stuff right here, embeddings. And now for each of these embeddings, we want to predict what is the next token, right? That's the question. Like, what is my next token that I want to generate? Well, let's go ahead and add that in. That's our head, right? So we can do finally pred, our predictions, is going to be self.head. And we're going to pass in here target embeddings, print pred.shape. And this should make it clear what we're trying to do. At every time step, we have 32,000 possibilities for what that next token could be. And so there you go. There's my, for every sample, for every time step, I want to predict which one of these 32,000 tokens is my next token. And because we've done this, we're basically good to go, right? This will turn into a probability vector when we do the softmax and all that later, or, you know, cross entropy and all that later. But for now, we're good. We have effectively written the training loop for our, or the forward function for our entire model, and we can return pred. So something different, I know we did a little bit of this in the ResNet implementation, but when you do these kind of more complex models, it's good to imagine your model as a bunch of these sub-modules and kind of imagine like, oh, how can I chunk my model up? We could have obviously written one transformer model with all of these layers inside it, but it wouldn't look as nice and it wouldn't be as readable. So this just makes it very convenient to work with. So now we have everything we need for our forward function. Good. Next up, we need our generative function, right? How do we inference this model? So let's go ahead and write that. We're going to do def inference self. And we're going to provide, when we inference, what do we have? We have English, right? So we're going to give it the source IDs, the English IDs. And we have no French, right? The French is the thing we want to generate. So that's what we're going to do. So, but we do need to let it know a couple things. So we're going to say target start ID. So if we look at our tokenizer, our start ID, our beginning of sentence is 2, and our end of sentence is 3. So start is 2, end is 3. We're going to need that. So we're going to say start ID is 2, and our target end ID is 3. And also max sequence length, right? What's the maximum that I'm willing to generate? There we go. So we provided English IDs and this stuff here, right? Basically the start of sentence, end of sentence. Because again, remember, every single thing that we are training, every French that we're training will already have a start ID and end ID on it, because in our tokenizer, we dictated that, right? We put a BOS and EOS token in our template processing, right? So there's always, French always starts with a BOS and always ends with an EOS. So there we go. We now have our start and end, and our target IDs, right, will be a tensor, torch.tensor, target start ID, because our tensor, when we haven't inferenced anything yet, right, that's the starting point, the starting ID, whatever it is, it's 2 in this case. And we can also throw a at torch.noGrad decorator on here, because when we inference, we have no reason to calculate any gradients on anything in this function. So there we go. And we can do device is equal to source.device. So we are source IDs.device. We want to make sure when we're creating this tensor, it's sitting on the same device where this is, because if this is on the GPU, then we got to make sure everything's there. And we can do dot reshape batch size by sequence length, right? That's what it is. In this case, we are doing, this is inferencing for one sample at a time. You could also do a batch inference, but that makes this a little bit more complicated and I'm not worried about it right now. So this is batch size by sequence length, right? We have just one token in this case. So we can print target IDs. And let's take a look at what this would look like. So what we want to do is t.inference English, right? We want to inference English. Let's take a look. And there we go. This is my starting point at 2, right? Because that's my start ID. So we're good to go there. Now what we're going to do is we have our source IDs, right? So we have our English. We just need to repeat this portion right here. We take our English, we encode it, right? So there we go. We have to convert our English to embeddings. And once we've converted our English to embeddings, we pass it through all the encoder layers, right? So all of this stays the same. In this case, there is no attention mask, right? Because I only have, again, this is something I'm inferencing for a single sample. So I'm only inferencing one sample, so there's no need for an attention mask here. So we can just ignore that, right? Attention mask is none. If we were doing batch inferencing, then you would need it, but I don't want to make it more complicated than it needs to be. So if we print source embeddings.shape, we should get a 2 by 32 by 512, right? So this is my embeddings from my encoder, right? Embeddings from my encoder. So we're good to go there. Now it's time to generate. So we're going to do for I in range max len. So I can only generate up to max, I called it max len. So let's just keep it the same as my online implementation. So max len, right? We're going to loop through one sample at a time. And basically we can only generate up to max len. And technically it should be max len -1 because we started already with the target ID. So we can only generate up to 511 more tokens, right? Because we've already just added the first token, which is the start ID 2. So okay, that's fine. This isn't actually that I should figure. Yeah, okay. By the way, that's fine. So first up, we need to embed these target IDs, right? So in this case, the target IDs is just this one thing, so there's nothing there. But we can do target IDs, or target embeddings. Actually, we can just copy it, right? We have this. Target embeddings is our target IDs. So there we go. Right, we pass our target IDs into our forward target. Just like before, right? We need to embed and add the positional information, in this case, to just our single 2. There's nothing there, right? So there we go. That's our target embeddings. And now we're going to do for layer in self.decoder. We're going to do target embeddings is equal to, again, layer, source embeddings, target embeddings. We're gonna, we want to figure out what the next token should be based on my current tokens, target embeddings, and context from my English embeddings, right? That's my extra context I need to do this generation. So again, exactly the same as what we had here before. It's just in this case, we're just starting with a single token 2 for our target. And once we're done, so we can go ahead and print target embeddings. I'm gonna throw a break in this loop for now. And I'm gonna move that up a little. So let's see if there's any issues. Looks like there is. Target.reshape. All right, let's see what could be wrong. Error. Shape 2x1x84, 8x64 is invalid for a size of 512. Okay. Let's take a look. So, okay, this is why we debug. So let's look at our attention implementation here. We're looking at it for qproj target, so that has to be this one right here. So let's just print out x, actually no, we want to print out target.shape. So let's see what it is. It's a 1x1x512, which makes sense because we only have one in this case. And we converted it to a 2. How did 2 show up? Oh, yeah, of course. This should be 1x32 because we're only doing one sample at a time, right? So let's see now. There we go. Yeah, okay. Yeah, so obviously I said this batch inference will only work assuming that you have a single sample, like we're not doing batches. So this has to be a 1x32, not a 2x32. Okay, so let's go ahead and delete this. Okay. All right, sorry about that. So yeah, we keep moving. So our target embeddings, let's run it again. Target embeddings, oh, dot shape, not helpful to see that. And there we go, 1x1x512, right? That's my encoded output for my transformer. So we're good to go there. And now we project a token, right? That's the last part. So we're gonna do pred is equal to self, actually one important idea. Let's, it's clearest if we draw it out. So we pass in first our start token, right? Beginning of sentence token. And we do all, and we have our, English, context, right? Whatever it may be. And we do our cross attention and we do everything. And we will predict something for this, right? Like we're going to predict the first French word, like F1. And so that means to predict the next word, we're going to put this here, F1, and then we're going to predict F2. And so, okay, then we'll put this here, f2 predict f3 dot dot dot, right? That we've talked about this. So that's the process. Now the thing is that when we pass in BOS and f1 to predict f2, we only need this thing here. We don't need BOS anymore, right? We only need the last time step to predict f2. Similarly, when we pass in BOS, f1, and f2 to predict f3, I only need f3 at the end to do this prediction. So I can go ahead and just clip my, or cut out the piece that I need. So all I need after all of this stuff is the final one. So we can do target embeddings is equal to target embeddings minus 1. We'll just grab the last time step because it's the last time step for which we want to predict the next token. But that last time step is a context vector of how it was related to all the previous time steps. So that's the important part, right? So the last time step, this f2 vector here is how it was related to f1 and BOS and itself and the English stuff, right? So it's a full context vector that has all of this information in it. And we only need this last vector here to do our next prediction, and so on and so forth. So we can always go ahead and just clip out the piece that we need and now do our prediction. So again, we can do our pred is going to be self.head target embeddings. There we go. Pred is equal to self.argmax. And why are we doing an argmax? Because we want to find out which embedding has the largest logit. And the thing with the largest logit is also the thing with the largest probability, right? The largest output. So whatever's the largest output is the thing that we want, and it is our prediction for this time step. So axis equals -1. But we're going to do a dot unsqueeze. Actually, let's just print out the shape. Print pred.shape. So this should be our has no attribute. Oh, shouldn't be self. It should be pred.argmax. Sorry. And actually, we can print out pred. So in this case, obviously this model has not been trained. Axis. There we go. This model that has not been trained has predicted token 21,422 as the next token, right? Now, the thing is that if we look at our print our target IDs, right? So the target IDs is our starting point. So given our source context and the beginning of sentence token, we predict that 17,933 is our next token. So there we go. But notice that our input has 2 dimensions, like it's a 1/32. So we have that batch dimension in there, but our target, the new prediction that we just made is just 1 dimension, right? It's just a number. So we can quickly just add a dot unsqueeze 0 to make them the same. So we can concatenate them together, right? So there we go. Everything is there. And so we have predicted this as our new target ID. So let's go ahead and do target IDs is equal to torch.cat. And we're going to concatenate this target IDs. We're going to concatenate our new prediction onto the target IDs and along the last dimension, right? Not along the batch, but along the sequence dimension. And we could print target IDs. There we go. So we can do print target IDs. Let's take a look at that. And it should look familiar, right? Here are my 2 predictions, 2 and then 7, 8, 4, 9. If I do it again, it should be different every time because this model is not trained, so it doesn't know what the next token should be. So there is our prediction. And if we repeat this over and over again, it'll just keep, adding more and more stuff to it. So this is how it's writing. This is also, see how it's like writing as it's going? Like it's literally, you can see it generating. This is how things like ChatGPT generate. They're just generating 1 token at a time. So there you go. There is our generation, right? Nothing too crazy. The question is, what if I don't need 512 tokens? Like, what if this is a short sentence and I only need like 4 French words to generate it? How do I know when to stop? And well, this is how we do it. We use the end token. Remember, the French data looks like this. You have a input is going to be our beginning of sentence, and then you have a French 1, French 2, French 3, French 4. And BOS needs to predict French 1, French 1 needs to predict French 2, French 2 needs to predict French 3, French 3 needs to predict French 4, and French 4 needs to predict the end of sentence token. So the model needs to learn, when do I stop? Again, given the context of the English and given everything I've generated so far, how do I know when I need to stop generating? And this is what the end of sentence token is used for. So what we can do is check. We can print target IDs, or sorry, we can predict our prediction, the thing we predicted. We can check if it's equal to our target end ID. Let's throw a break in there, right? So did we just predict a end ID? Are we done? Is the question. So if we look at this, it'll return a kind of a nested true false like this, right? In this case, it's false because it's not the same. And so just a quick thing we can do instead of indexing is torch.all. In this case, torch.all doesn't matter. We're just comparing one thing to one thing, but we're just checking, is this thing a true or is this thing a false? In this case, you can see it's a false because we are not at the end of sentence yet, and we probably won't be because we haven't trained this model yet. So we can do if this is true, if we have gone ahead and generated a target end ID, as in this is the end of my sentence, end of my translation, I can go ahead and break the loop, right? That means I am done. Again, this won't help us right now because if we do print target IDs, as it starts to generate, right, it'll generate and that's totally fine, but the likelihood of it predicting the 3 is unlikely because it hasn't learned anything yet, right? It doesn't know anything. So it's just going to generate, and we just set the max length as 512 minus 1. So there we go. But the final question is, I'm going to set this to 64, or I don't know, let's do 8. So we don't have to keep seeing that over and over again. We'll change it back. And so let's go ahead and do, let's see here. Right, so we're going to do return. What we want is the tokens, right? Well, in the end, all we care about is the tokens. What were my predicted tokens? And then we'll use the tokenizer to return it back from tokens to our French, right? Like the actual French. And again, this is why we wrote in our tokenizer decode, right? To take our French and convert it back to tokens. Or back to, French, the text. Take our tokens back to French. Okay, so there we go. What we're going to do is target IDs dot squeeze. So squeeze will remove that extra batch dimension because we don't really need it anymore. We're going to move it to the CPU just in case we were inferencing on the GPU, and we're going to just convert it to a list. Okay. Okay, sorry. So we're going to go ahead, convert it to a list, and we are good to go, right? This is our final implementation of this transformer. Last up is, okay, so our model's done, everything's done. If you made it this far, great job, because this is basically every transformer looks like this for the most part. So if you've done one of them, you've kind of done all of them. We do need one more thing. I'm just going to copy paste this in because I don't want to type it, but I will explain it. Weight initialization. So all these weights are initialized as something like all our linear layers and whatever. I mean, we only have really linear and embedding layers here. They're all initialized in some way. Transformers seem to like slightly different initialization from the default. Typically, they like being initialized with like normal distributions with, some small standard deviation and that sort of stuff. So this is just directly taking for the Roberta implementation. It's just initializing every linear layer, every embedding layer, and all our layer norms with these, normal and whatever. So nothing fancy. I'm not going to go into it too much. How we use this is we can do in our transformer is we can do self.apply init. Oh, was it 1 or 2 underscores? Oh, it was 1 underscore. Init weights. Okay, good. So we have our model completed. We have everything we need completed. And yeah, this is actually pretty good. So yeah, we have our model. Now for the final part, we have a model, we need to train it. right? So just like before, what I've mentioned, whenever I train models, I am going to basically always use the Hugging Face Accelerate platform, because training on one GPU is not that interesting. Training on multiple GPUs is interesting, but Accelerate means that all the code I'll write can be run on a single GPU if necessary, because you can just change the config file. So I have a whole video on Accelerate, reproducing the ResNet 50 model, which I'm not going to go into again. So we're just going to go ahead and write a train function. So train.py. So this won't look all that different from any other train function we've done. So we're going to just go ahead and do it. So we need import OS, import numpy as np, import torch, from transformers, import auto tokenizer. So this is where our BERT tokenizer is going to come from, and a get scheduler. We need a learning rate scheduler, so that's fine. From torch.utils.data, import data loader, right? And we can do from accelerate, import accelerator. We need to also load our data set, which we've already said. So from datasets, import load from disk. So there we go. And we can do from TQDM, import TQDM. Right, so we need a progress bar. And lastly, for the stuff that we wrote, we're going to do from model. We're going to import in the transformer and the transformer config that we wrote. From data, from the data set that we wrote, from data, we're going to import in the translation collator. And from tokenizer, we're going to import in our French tokenizer. So again, if you are confused about any of this stuff, just watch. I implemented all this stuff in the previous video, so I'm not going to talk about it again. But yeah, it's all there, so just take a look. We go into a lot of detail in how those came on. And we're also going to set an environmental variable here, environ. This is tokenizer's parallelism equals, and this needs to be in brackets, false. This is basically when we use the Hugging Face tokenizers, we're already going to be doing it in a distributed way, because there's multiple GPUs and multiple CPU cores doing everything, right? Everything's already distributed. And the tokenizers are also distributed, so this will just throw a warning, an annoying warning over and over again that, hey, like you're trying to do a distributed thing on a thread that's already distributed and it's not happy. So we're just going to keep it like that. Okay, so we're going to do encoder depth is equal to 6. Decode, actually we don't need to, well, I can go ahead and actually copy this because there's nothing interesting here. This is just all the config stuff that we've already talked about, so we don't need to talk about it again. So basically, what is my encoder depth? Everything that was in that config file. It looks like I do use a slight dropout. We actually don't have that much data. I think it's like 15-ish gigabytes worth of data, so fine, we threw a dropout in there. But there we go. There is all of our model config. We have our tokenizers. My French tokenizer is just going to use the French word piece that we made earlier. And my auto tokenizer, we're just going to use BERT, right? Lowercase BERT. So there we go. My path to data might be incorrect though. Let's double check that. So in data, my path to data will be this, HF tokenized. So let's copy that in. There we go. What batch size do I want to use, and how many gradient accumulation steps do we want to use? This is, I have enough GPU memory for this to not matter, but this is just for learning, so I'll make sure I implement it. And then how many CPU workers do I want? I'm going to do 32 workers. And then training config, normal stuff, right? Learning rate, how many steps do I want to train for? How many steps do I want to warm up for? What scheduler do I want to use? You could really explore any scheduler here. I always use cosine for transformers, and it seems to just work, so I don't worry about it. And every 2,500 steps, I want to evaluate the model. Let's make this 250 steps for now, just so we can actually see it happen. Bias norm, weight decay. I'm going to ignore some of these little complexities. You can take a look at my accelerate thing to see that typically you don't want to apply weight normalization on bias parameters, but I'm not going to deal with any of these little things right now. I want to focus on what we're focusing on right now. Weight decay, betas, atom EPS, and I believe I got these betas from the original paper, so you can just go look there. So okay, we're good to go. we're going to create a workdir. I'm going to create a new folder here called workdir, where all of this stuff will be saved. Here's my experiment name, logging interval, that sort of stuff. Okay. And we're not resuming from any checkpoint because we don't have a checkpoint right now. So first step, wow, okay. Training script, right? We're going to write our training script now. What we're going to do is our path to experiment is going to be os.path.join between our working directory and our experiment name. And so we can initialize our accelerator is equal to our accelerator at our project dir. The project directory is just going to be this path to experiment, and our log width equals weights and biases, right? So we're going to log our experiment width and biases. And actually, just to make this, I'm just going to call this seek to seek because I already have a log in weights and biases that I don't want to mess up. So we're going to just keep it like that. Okay, good. So we have our training script, accelerator, and then accelerator dot init trackers. And we're going to do it the experiment name. I'm going to comment this out for now. So we don't really care about weights and biases, to be honest. So I could probably just ignore it, right? Because it's fine. If you want to use weights and biases, just uncomment this and it'll run, right? But in this case, I'm not going to do it. Just keep it simple. So our config is equal to transformer config, and it's just going to be all the information. Embedding dimensions, embedding dimension. Our num attention heads is num attention heads. Our attention dropout is attention dropout. Our what else do we have? We have our hidden dropout is hidden dropout p. Our MLP ratio is the MLP ratio. Encoder depth is encoder depth. Decoder depth is decoder depth. Our source vocab size is the source tokenizer dot vocab size. Right, so I know I had a default in there, but if for some reason your tokenizer is slightly different, then it'll load it from here, right? So my source tokenizer.vocab size. And then similarly, our target vocab size is going to be our target tokenizer.vocab size. And this is exactly why in our tokenizer, when we implemented it, we added this extra attribute of the vocab size. So there we go. Anything else that's important? Right, so max source len is going to be our max source is equal to max source len, and then max target len is max target len, which we know is both 512, and then learn pause embed is learn pause embed, right, which we don't want to do. So there's our config. Let's go ahead and prepare our data loaders, right? Data loaders, that's this part. So we're going to do our data set is load from disk path to data, and let's just double check this worked with the path. So now we want to run python train.py. And there we go. There's our data. We have about 40 million examples of for training and about 200,000 samples for validation. So we're good to go there. Now that we have our data set, we want to make a data loader out of it, right? So we can do accelerator.print dataset just so we can see it as we're going. And we're going to do our collate function, right? So again, the collate function is how do we take samples, put it together. We're going to pass it the source tokenizer and the target tokenizer. So again, our collate function, which we write in data here, is the logic of grabbing a batch, processing it, and providing me the data that I want. My English IDs, my tokenized English, my English padding mass, my input French, and my output French, so the offset French, and its corresponding padding mask. So all of that information can be found, or can be created via the collate function. And as we start implementing more complex models, I think the best example is when we do the wave to vec2 implementation, probably in a few weeks. The collate function is the toughest part of that implementation. That collate function, how we prepare, batch, put together data is really what becomes complicated, and the model kind of stays pretty stagnant as we go through it. So either way, here's our collate function. Let's go ahead now and do our data loader. So for our data loader, we need a batch size, but in case we're doing some mini batch size, in case we are doing gradient accumulation, right, our batch size will really be the batch size that we want divided by the gradient accumulation steps, right? So that's because that's all we can fit. So that's what we're gonna do. And so our train loader train loader is going to be a data loader. On the data set, on the training split, our batch size is going to be the mini batch size. Our num workers is going to be our num workers. Our collate function to stick things together will be the collate function here. And shuffle will be true because we like shuffling our training data. Similarly, our test loader is going to be a data loader, data set, but now it will be on the testing split. Okay, test. Sometimes it's called val, but I called it test, so there we go. Our batch size, again, batch size is the mini batch size. So there we go. Our collate function is the collate function. And when we're inferencing, we have no need to shuffle. So we can set this to false. So we have everything we need. Now it's time to prepare model. Right? So our model, very simple. It's the transformer that we wrote. Transformer, and we just give it the config. And what we're going to do is model dot, we want to print out how many parameters does this model have? Like, what are we training here? So we're going to do model parameters is equal to, we're going to first filter, granted everything in this model, except for those, actually the sine, cosine embeddings. Everything else is trainable. So we're just going to filter for dot requires grad. Model dot parameters, right? So we're going to filter out our parameters just to see which ones we have gradients on. And params is just going to be the sum, right? We're just going to add up np dot prod. Actually, I don't want to do it that way. We can do, actually, let's do it a slightly easier way, or more readable way. We can do total is equal to 0 for param in model dot parameters. If param dot requires grad, right? If it's true, then we're going to do total plus equals param dot number of elements. And if we take a look here, we should see that we have 92,565,760 models. So it's a parameter. So this is basically almost 100 million parameter model, which isn't too bad. It's a pretty reasonable amount for something like this. So, okay, I'm going to go ahead and delete this because, well, actually, it's fine. We can do accelerator.print number of parameters total. Right, so we're going to print out how many trainable parameters we have. Now it's time for our optimizer. So our prepare optimizer. So this is, again, where I have this additional little bit of complexity. I'll just show it real quick, but we won't use it right now. In the optimizer, I add this extra flag of whether or not you want to do weight decay on the bias or not. We do this in the ResNet one, and we should probably do it here, but it's fine. I don't think it actually affects performance in any meaningful way. We're just going to ignore it for now. If you need it, just go look at my implementation online. It'll be linked in the section below and in the description below, and it's fine. But for now, we're just going to do optimizer is equal to torch.optim.atomw. So, you know, with our, we're going to be adding in our weight penalty. We want to do it on the model.parameters. With a learning rate of whatever learning rate we pick. Betas will be our betas, right? Whatever the betas are. I just took them from the paper. And then EPS is atom EPS. That helps with like the divide by 0 error and that sort of stuff. So there we go. Good. So that gives us everything we need on the optimizer. Lastly, we need our scheduler. So scheduler, we can do scheduler equals get scheduler. Name is equal to scheduler type, which was just cosine in our case. The optimizer is going to be our optimizer. Our num warm-up steps is going to be the number of warm-up steps that we pick. And our num training steps is going to be the training steps, or training steps that we pick. So there's our learning rate scheduler, right? Nothing fancy. Lastly, loss function. So next token classification is still classification, so it's still cross entropy. So loss function is torch.nn.cross entropy loss. So nothing changes there. And what I'm going to go ahead and do is define a sample sentence just for testing, right? So every once in a while, we're going to go ahead and see what something generates. And so we're going to do define sample for testing, right? So whatever. I'm going to call this source IDs. So the thing I want to predict is going to be torch.tensor. I'm going to pass in with the source. We want to convert our, let's say, I want to learn something new, right? And we're going to just grab the input IDs from there. And there we go, right? That will, and we'll add the batch dimension in artificially. So unsqueeze dot unsqueeze. So there we go. And we can go ahead and prepare everything. Right, so this is now going to be our model, optimizer, train loader, test loader is equal to accelerator.prepare, model, optimizer, train loader, test loader. Right, so there we go. And we can do accelerator.register for checkpointing our scheduler. Right, so we can also make sure we checkpoint this. So if you're training your model over you train for a day and then you stop and then you want to pick back up, this way the scheduler also picks back up from the checkpoint that we make. So there we go. And so we need to first write a resume from checkpoint. Script. And actually, one thing we need to do is if we're training on multiple GPUs, we actually need to throw the scheduler in here as well. Scheduler. If we're training on multiple GPUs, we actually need to scale this by accelerator.num processes because every operation happens multiple times, right? So we just need to make sure that we scale it up for however many steps we do. It's still doing the same number of steps, right? We're only going to train for 100,000 steps, but because we have 2 GPUs that I'll be training on, this scheduler will be called 200,000 times. So we just need to double it up so everything happens twice. So there we go. So we can now do if resume from checkpoint is not none, right? So if we're actually resuming from checkpoint, we can do path to checkpoint is going to be os.path.join between our path to experiment and our resume from checkpoint, like whatever checkpoint we pointed to do it from. And we can do with accelerator.main process first, which is just recommended by Hugging Face, that when you want to do accelerator.load state path to checkpoint, you just do it with the main process first. And we'll set our completed steps is equal to, so our checkpoint, I like saving them like this, like checkpoint 100. Right, something like that. So what we're going to do is just do our resume from checkpoint. So resume from checkpoint would be checkpoint 100. I'm going to do dot split on the underscore, so it only it becomes a checkpoint comma 100, a list. I'm going to grab -1, so it grabs the 100, and I'm going to convert it to a integer. So there we go. That tells me how many steps I've officially completed. And we can do accelerator dot print resuming from iteration, and we can put completed steps in there. Else, right? Otherwise, if we're not doing it, then completed steps is 0. Like we're just starting from the beginning. We haven't completed any steps yet. Great. Now it is time to go ahead and write our training loop. So how we're going to do this is we're going to set train as true, and we're going to create a progress bar. It's going to be tqdm range completed steps to training steps, right? So in the case of if we just start, then this is just going to go from 0 to whatever. But if we're not just starting, then we're going to start from there. So there we go. And we're going to do disable is equal to not accelerator dot is main process, right? So we want to go ahead and not print out tqdm twice because we only need it for the main GPU. So there we go. And we're going to do while train, so this will always be true. We can do accumulate steps is 0. So how many accumulation steps did we do? We will have a accumulate loss equals 0, and accuracy equals 0. Right? So we're gonna keep track of this stuff as we go. And the reason I'm doing an accumulate steps here, which looks different, is when we did the ResNet and accelerate implementation earlier, we used the Hugging Face accelerates, like the accelerate has a model.accumulate, like it has an accumulator, it does it for you. We could use that, but I think it's more beneficial to kind of be flexible, and later will be we need some more control over what's going on inside that accumulation. So we don't want to automatically accumulate it. We can do it ourselves. And so we're just going to do it ourselves. So how do we do this? We're going to do for batch in train loader. And remember, our train loader, the batch size that we picked is scaled down. So if our batch size is 256 and we want 2 steps, really we have to do 2 steps of, or if we want 2 accumulation steps, we have to do 2 accumulation steps of 128 to get to the 256 that we want. So we have to basically do, if we have 2 accumulate steps, we have to do 2 batches, so 2 loops in this, to get to the steps that we want. And so that's what we're going to do. We're going to do source input IDs is going to be batch, source input IDs dot to, and we're going to put on the correct device, accelerator.device. So there we go. So again, the output of this is going to be source input IDs, source pad mass, right? This is all the stuff that's going to be in our batch. So that's what we're going to grab. We're going to need this. We have 5 things, so we're going to have this 5 times. And the second one will be the source pad mask, and then we will have our target input IDs, and then we will have our target pad mask, and then finally we'll have our target outputs, right? The thing we want to predict. So there we go. And we will just copy all of these into here. So there we go. That will give us all of our data. And so all we have to do is take all of this and give it to the model. So we're going to do output. Output is equal to model, source input IDs, target input IDs, source pad mask, and target pad mask, right? So again, we wrote the model, and we wrote our transformer, and we provide to the transformer the source, the target, the source mask, and the target mask. So that's what we give it. And everything else is done for us because we wrote it already. And so we can print out the output.shape here. I'm going to throw a train equals false, so it breaks, and then break it, right? So let's just break it. And let's take a look here. Let's see if we get any bugs first. So now's a good time to debug. Looks like we're missing a dim. So this should be unsqueeze 0 because we're adding in a batch dimension. So there we go. Up next, what's our next problem? Oh, no problems. Okay, good. So we've outputted a 64 by 266 by 3200 tensor, right? And one important thing to keep in mind, again, if we look at our data, we've replaced all our, so let's be clear here. I mentioned this in the last video, but it's important for anyone who's just joining on this one. We have a, so beginning of sentence, French 1, French 2, French 3, French 4, and then we could have a pad, right? That's what it is. And let's say, no, actually, let's make this clear. If we had this, we'd also have a end of sentence, and then we'd have a pad, right? We have some padding tokens that we have to add because we have to fill the batch out. So that's always going to be there when we're training. And so BOS, what are our targets? BOS needs to predict F1. F1 needs to predict F2. F2 needs to predict F3. F3 needs to predict F4. F4 needs to predict F5. Or there's not 5. F4 needs to predict end of sentence. You are done generating, right? So given BOS, this is what we do. Now, what about after this? What does EOS need to predict? Technically nothing, but we have stuff here, and because everything is batched, it's going to calculate on it. So this is why we set these labels, everything after this, to -100. So when we compute the loss function, cross entropy loss ignores -100 labels by default. So by default, cross entropy loss will not calculate any loss on these terms and only on these terms. So it'll only do it on the stuff we care about, and it'll ignore it on the stuff we don't care about. And just so we can see what this looks like, right, we can take a look at our train. Let's look at the target outputs. Target outputs. And you'll see here immediately, once it's done inferencing, here's those -100. So on these specific labels, right? So everything here, the model has to predict. Like it needs to predict this is the next token, this is the next token, this is the next token, yada, yada, yada. But on these tokens, they're -100s. We have no interest in calculating them. They're just pad tokens. So anything that's a pad token, we ignore them, and there you go, right? So again, in our tokenizer, in our data set, we specified this. Anything that is a target pad token in our output is a -100 because it doesn't make sense to predict pad token. Pad tokens are, again, just fillers that don't mean anything. Okay, good. So we have all this. So how do we do the rest of this? I'm going to leave that break in there because it's convenient. Oh, don't need two of them. Double vision. All right, so now we have, okay, so output is equal to output dot flatten 0, 1. All right, we're going to flatten it out. So now we can do print output dot shape. And let's also do our targets. Targets is the same. TGT outputs is equal to TGT outputs dot just flatten. So we're going to completely flatten this one. And it will make sense when you look at the shapes. TGT outputs dot shape. And this looks like this. And actually, to make everything go a little bit quicker, let's do a batch size of 4. Right? Let's do a batch size of 4. Let's make everything go a little bit quicker. All right, so we have 50 time steps, right? We flattened it, so we have 50 time steps across all the sequences. So actually, maybe it'd be best for me to print the output.shape beforehand, before we do the flatten, so we can see the transformation. So we have our 2x39 time steps, right? So we have 2 samples, each with the sequence length of 39. With, you know, they have the respective padding tokens. And so I just take all of these because I just want to calculate the loss independently, like every word independently. So I can take the 2x39, flatten it to a 78. So there you go. Now we have 78 by 3200. I have, for each token, I have 32,000 possibilities of what that next token could be. Here are the 78 correct answers of what those tokens really are. And that's all. So we can go ahead and just calculate our loss function with that, right? This is exactly what the cross entropy loss expects. Okay, so we can do loss is the loss function between our output and the target outputs. So there we go. And now the important part, we want to accumulate these losses up, which means we're actually taking like the loss of the first batch and then the loss of the second batch and the loss of the third batch, and we're just going to average those losses together. So we're going to do loss. I don't need to do that. We can do loss is equal to loss divided by gradient accumulation steps, right? We're going to scale our loss to the steps. So if we do 50 steps of gradient accumulation, then we need to average all those losses together. And so we divide like that. And we can finally do accumulated loss plus equals loss. We're going to go ahead and store those losses in there. Next, we're going to compute our gradient. We can do accelerator.backward loss. So in they will automatically scale the gradients for us, right? Or actually, that's not true. If we use the accumulate, like the accelerator.accumulate context manager, like we did in the ResNet, then they'll scale the loss for us. In our case, where we are scaling the loss ourselves. And so dot backwards will compute the loss, but we're not going to zero out the gradient yet. We're going to repeat this whole operation over and over again until we reach the batch size that we want. So there we go. We have everything we need. We can also compute our accuracy, right? So output is equal to output.argmax, axis equals -1. So what is my largest logit, which is my prediction? but we want to compute the accuracy ignoring our mask, right? So we're going to, or ignoring our padding, so because the padding doesn't mean anything. So we're going to do mask is equal to target outputs does not equal to -100. So where are my targets, not this kind of extra mask padding thing we have. And we're just going to go ahead and filter our output for this specific mask. And we're going to filter our target outputs for this specific mask. Right, so we're just going to make sure we get, so again, if we look at the shape, of these 78 tokens, some of them are mask, right? Some of them are these -100 masks. And we don't want them, so we're going to create a Boolean vector here of length 78 that are true and false for which ones are things we want and which ones are not the ones we want. And then we just filter out these 78 for all the trues, and we filter out these 78 along with their 32,000 for all the trues, right? So we just filter things out for the non-100s, and that's it. Nothing crazy. Our accuracy is going to be output equal target outputs dot sum divided by len output. Now, when it comes to these generative problems, there's actually multiple ways you can transcribe a sentence, right? Like there's multiple ways I could say a French thing for the English, right? There's multiple translations. So accuracy is not really a good metric. There's other metrics out there like the blue score and stuff like that that you can look at. I'm just doing accuracy as something easy that we can keep an eye on as it's training, because it should go up. Like we should see some reasonable accuracy. So accuracy is going to be plus equals, again, acc divided by gradient accumulation steps, because we want to average it over all the steps. And we're going to accumulate steps plus equals 1. So we have completed a single accumulation step. If accumulate steps is divisible by our gradient accumulation steps, that means like if we have 2 gradient accumulation steps, if our accumulation steps is 2, so we've actually completed 2 full steps, then we can now go ahead and actually update the model. So up first is we need to do accelerator dot clip grad norm, right? We wanted an on the model dot parameters and a max norm equals 1.0. So this makes sure that none of our gradients are some ridiculously big value and messes everything up. So we're going to clip our gradients here. Next, we're going to do optimizer.step, right? We're going to we've computed gradients, right? We've just accumulated up the gradients for all those gradient accumulation steps. Now that we're done, there's gradients in our data, in our model, we can go ahead and update our model. Once we've updated the model, we can then do optimizer.zeroGrad, just like always. Zero out our gradients, and for efficiency we can do set to none equals true. So instead of setting all our gradients to 0, we can set them to just nones. And then scheduler dot step, and there we go, right? We are going to take a step in our scheduler, and we're going to now do if so that's it. That's our update step, right? That's it. And once we have completed an update step, now we can do the rest of the like kind of logical things that we need to do. So first of all, we're going to do if completed steps is divisible by evaluation steps, right? So if we're finally ready to evaluate the model, which I said every 250 we'll do it, we're going to do model.eval, throw it into evaluation mode. We're going to print out, let's just accelerator.print evaluating, just so we can see it's happening. And then we can do test losses as an empty list, test acts as an empty list. And the rest of this stuff is actually identical to what we just did, so I'm just going to go ahead and copy paste it. Actually, wait, no, I'm missing one. Actually, okay, that's technically fine. Okay, let's do it in order. So we actually had another statement here before, just so I can make sure I'm doing it like my code online, so anyone referencing both is not confused. We're going to accumulate steps, percentage, logging interval is 0. So how often do we want to log our model, right? And then, so we log the model, and then we also have our gradient accumulation, all that stuff. So let's go ahead and do this. We're going to do accumulate loss, or accumulate loss is going to be accumulate dot detach, right? We no longer need this on the grade because we've already updated our model, right? We've already gone ahead and updated our model. This is my bad. This needs to be inside here. Oh, I guess I didn't copy it correctly. Okay, one more time. If completed steps percent logging interval is 0. First up, we need to do accumulate loss is equal to accumulate loss dot detach. We're going to take it off our gradient information. We don't need it anymore to be a part of the computational graph. Similarly, accuracy is going to be equal to accuracy dot detach. Right, so there we go. And we can go ahead and do if accelerator dot num processes greater than 1. So if we're using more than one GPU, then we need to pull all this information together, right? Grab it from all the GPUs. And we can do accumulate loss is equal to torch.mean accelerator.gather for metrics accumulate loss. And then our accuracy is going to be torch.mean. Same thing. Accelerator.gather for metrics. In this case, the accuracy, right? We're going to just grab everything off of all the GPUs, accuracy, and then average them up. So there we go. Now we have our average loss and accuracy across all the GPUs, and we can then go ahead and just do the rest of this, which I'll just copy paste. There's nothing here. Basically, go ahead and create a log. Accelerator.log will push it to weights and biases. So we're going to log our loss, accuracy, and the training rate, learning rate. We're going to go ahead and print this to our terminal, and then we're going to we can also write this on our progress bar, right? So that's how we're doing it. So there we go. If we're in evaluation mode, I can actually paste this code too, because nothing new is happening. The evaluation code looks identical to our training code. So let's just go ahead and copy it in. Again, nothing happens. So if we're evaluating, right, if we're on an evaluation step, throw the model into evaluation mode, loop through our testing loader. We're going to only do this in inference mode or with torch.grad, either one's fine. We're going to go ahead and flatten, compute our loss. We're going to compute our accuracy, store the results. Again, gather over the multiple GPUs, nothing new, and then store these metrics. And that's it, right? So again, nothing fancy. And I believe we created up here, I think I forgot to create some, oh no, we're good. We're good. Yeah. So we're going to store them in these two lists here, average them up, again, store them, log them, send it to weights and biases. And this is where I will go ahead and save my checkpoint, right? So I'm going to go ahead and save my checkpoint at this point. Every evaluation steps, I'll checkpoint the model. So there we go. And now we should probably go ahead and test a sentence, right? So we can just see what the testing sentence, right? Let's see what this looks like. So we're going to do if accelerator.isMain process, right? So if we're on the main GPU, we only have to do this once. Source IDs is going to be equal to source IDs.to accelerator.device. It will basically be the main device. Unwrapped. So whenever we use accelerate, it wraps the model in the DDP wrapper, which means we can't directly access things like .inference anymore. So we just have to unwrap the model, which just pulls it out of the DDP wrapper that it puts on it, and then use that to do our training. So we can do unwrapped is equal to accelerator.unwrap model. Basically, it basically adds some extra stuff in it. So if I went right now to do model.inference, it would say inference is not an available method because it's not, because the entire class has been wrapped in another class. Unwrap.model basically just returns the actual model that we wanted. So there we go. And so now we can do translated is equal to unwrapped dot inference source IDs. Target start ID is going to be, we know it's 2, and target end ID is going to be 3. Or if we want to be more general, like if you have a different tokenizer, then you can use this, right? We can grab the BOS and EOS tokens. Lastly, we can now unwrapped. There we go. Lastly, we need to do translated. This will return a list of numbers like 1, 10, 22, like whatever the predicted tokens are. So we can do translated is equal to tgt tokenizer dot decode, right? This is our tokenizer, or I thought it was. Maybe I called it something different. Let's see here. TGT tokenizer. Yeah, okay. Tokenizer. There we go. Dot decode our translated. Right, so translated. And we're going to do skip special tokens is false. Because when we decode, we don't really need the EOS, BOS tokens. We don't really care about those. So we made sure to exclude them when we wrote the decode function in our tokenizer. So again, questions, just look at the previous video. I talk about it there. And we're going to do if accelerator.is main process. We're going to go ahead and do progress bar dot write f translation translated. And there we go. And once we are done with all of this, we're going to throw our model back into training mode. Right, so we're going to throw our model. So we put it into evaluation here. We throw it back into training mode here because we're done with all of our evaluation and everything. And it looks like I do a save state. So my final thing will be if completed steps greater than or equal to training steps, right? So once we're done, we're going to set the train to false. We're going to do, again, accelerator.save state. And we're going to save it to os.path.join, the path to experiment. And we're going to say, we're just going to call this the final checkpoint, right? This is our final checkpoint. So when we're done, and we can break the loop. And because we set train to false now, this will exit and be done. Otherwise, we're going to do completed steps plus equals 1, right? So basically, once all of this stuff is done, if we've once we've completed a full accumulation step, we kind of go through all of these if conditions based on what we need to do. Otherwise, we're going to go ahead and iterate, right? We've completed one full step of accumulation, and we can do progress bar dot update 1, and then we can reset our accumulate loss to 0 and our accuracy to 0, right? Just reset them. So in the next accumulation, they'll continue accumulating again, and we can do accelerator dot end training. So let's go ahead and see how many bugs I just caused. So I think I need to do accelerate config. I set it to single GPU mode. If you need to know about these configs, just look at in my Hugging Face accelerate video. I talk about it there. No. 2 GPUs, 0 and 1. No. bfloat 16. There we go. All right, let's see what went wrong. Accelerate launch train.py and see what happens. So it's going to load the data. It's going to load the model. Len tensor size 90 must match tensor of 132. So let's see what's happening here. Okay, both of them are being masked. So let's just check here. Print output.shape, output.shape, and print target output dot shape. Output dot shape. Right? I'm still spelling wrong. Outputs. So there we go. We're going to do these, and that's all of these, and that's all of those. Okay, let's just check that. See what it does. See where the mistake is. So we have a bug that's expected. Wait, did I run it at the wrong time? this is line 1. Oh, this is an evaluation. Okay, we'll have to come back here. We'll have to do the same thing here probably, but let's go up here. This is going to be target output. Oh, whoops. I never saved it as a variable. So there we go. All right, let's see what the next bug is. Nice. It is training. All right, so this model will train then. Everything is working. We will pick a reasonable batch size, maybe 128, and go like that. And this model should just train away, right? So it'll just do what it does. We'll leave it alone. Now, you sitting here and watching a training script is not of interest to anyone. So let's just look at the final result of the model, because that's all that really matters, right? So up till now, basically, you have learned the entire transformer architecture for the attention is all you need paper. There's really not much more novelty for us to do here. So yeah, we are basically good to go. So let's go ahead and I see this is the evaluation loop. I guess it's going to do it right at the beginning because technically it is divided by 0. So there you go. It's going to evaluate the model. Anything else it'll do? It will also print out one of these testing strings, I believe. So yeah, it's fine. So this is slowing down my computer because I'm screen recording and training at the same time. Out of curiosity, we can take a look and see that, yes, indeed, both GPUs are being utilized, right? So accelerate is great, makes things very simple. Very few code changes necessary to a regular training loop to get it to be distributed, which makes our life very, very nice. So let's just let this full loop go through, make sure everything kind of works. Hopefully there's no more bugs. As you can see, the training accuracy is nothing because, well, it hasn't learned anything yet, right? So of course it's nothing. fp.write, no string object. I'm not sure what that is. Progress bar.write. Maybe TQDM doesn't have the write anymore. I'm not actually sure. That's okay. We can just do a accelerator dot print translated, right? So there we go. Either way, regardless, this is not of much interest to you at this point because this takes I'm not actually sure. I think it takes a few hours to train at least. So we're not going to worry about it too much. What I do want to show is the final results. So what I'm going to do is while this is running, while that's running, just to make sure it works, because I want to be as accurate as possible, we can cd into the NCSA. PyTorch for NLP, and we're doing sequence to sequence here. So there we go. And this is the original. Basically, this is the code that's sitting in the repository right now. Conda activate torch, Jupyter Lab. Okay, let me open up this inference script, which I have a feeling is not going to work directly because I have a model running. And do I even put it on the GPU? I don't think so. So let's just let's see here. Let's just let this loop finish real quick. But okay, I guess that's while that's happening. We can bring this here. Sorry, whenever you hit the GPUs and screen record at the same time, it is definitely not happy. Oh, okay, I shouldn't mess with it. I'm gonna stop this when it's done. So I'll just wait. There you go, right? So there's the prediction, and now it's training away, right? So you can see it's going to take about 20 hours, 18 hours to train 150,000 iterations. Not the worst, right? So this will train. Loss, you can see, is already starting to decrease. We're already starting to get some accuracy, so things are starting to predict. Either way, I'm gonna stop this because, again, watching this train is of no interest to anyone. We just want to look at this. So this is a model I've already trained for 150,000 steps, and I didn't do anything. I just loaded my transformer, loaded my weights into the transformer, load state dict. I then grab my French and English tokenizers, and I go ahead and translate, right? And I get Je vous apprendre quelque chose. I don't know French, right? So pardon my French is what they say. Either way, so this is the prediction. If I give this to Google Translate, you see it gives us the English back. And that's exactly what I gave it. So this model is somewhat verified. Now there are significantly bigger models out there that are much better for language translation today. There's multilingual models that can take multiple input languages and have multiple output languages, which is really neat. But either way, again, let's do a quick recap of everything. What we have learned today is basically we picked up from writing the datasets and data loaders last time. We wrote an entire transformer model from scratch. And this is super important to understand because every future model we do is effectively just a subset of this model. The vision transformer, for example, right here, the vision transformer, we just need this left portion here. The GPT and Llama and all these other generative models is basically this right portion here without the multi-head attention, or without cross attention. There's no cross attention in Llama. When we do diffusion, we're going to kind of have this cross attention set up again. So this is basically fundamental. Every transformer model you see today is some variant of this, right? They're basically taking this and doing some interesting change to it. And over the next, as many videos as I'm able to make, I want to explore those variants. I want to see how this is used for vision. I want to see how it's used for speech. I want to look at the different types of positional encodings because there's definitely better ones today other than sine, cosine, and length. There's rotary embeddings or alibi and other stuff. I want to look at different types of attention mechanisms. This attention mechanism has a huge quadratic penalty, which we're not happy about. So we have sliding windowed attention or sparse attention and other methods. Feed forward layers is where a lot of those parameters sit. Right? The way at least I like to think about it is the multi-head attention learns the relationship between every word, right? How words are related to each other. The feed forward is just a learned projection of those things. And so there's again, a lot of your parameters of your neural network are sitting inside those feed forward modules, which means that we don't really need to, there's other variants, some better variants of feed forwards that we can use as well. Namely, the mixture of experts comes to mind. Either way, this is basically it. This covers everything that I wanted to do for this introductory video on attention is all you need. I hope these 3 videos I feel like it adds up to almost 7 hours or 8 hours across all of them. I hope they're relevant. If you have any questions, comments, concerns, please drop a comment below. If I've done something wrong, that means I understand something incorrectly. So I've always wanted to be fixed. I always want to fix my own knowledge. But thank you, everyone. I will see you in the next video.